So there was a movie a number of years ago, National Treasure, where Nicolas Cage goes and finds a secret message on the back of the Declaration of Independence. And that implied that there were some really intelligent people that had figured out how to encode that message and so on. What if there was a secret code built into math, built into numbers, 1, 2, 3, 4? What if we discovered a secret code built into that? What would that imply? That would be fascinating, wouldn't it? Because that would imply that numbers themselves have a creator, and a very intelligent one, if we found a message built into numbers. And in fact, there is a code built into numbers. And it's absolutely amazing. It's mind-blowing. And this was discovered in the 1980s. So this is relatively recent. People have been using numbers for thousands of years. But it wasn't until the 1980s that we discovered there is a code built into numbers. And I want to share that with you today because it's neat. This is something that I read about when I was young, and it just blew my mind, and I want to share it with you. Because we don't tend to often think about God creating numbers. We think about God creating the earth and the stars and the initial organisms on the earth. But God is also responsible for numbers. Not that he created them in the same way, because they're not physical, right? Numbers are abstract, they're conceptual. They exist in the mind. And yet God is responsible for numbers, and he has embedded in numbers an amazing code of unbelievable complexity and beauty. And I think it's going to be mind-blowing to you. It's really going to be mind-blowing. When I was a little kid, my mother would prepare these wonderful meals. She's a very good cook. But occasionally she'd prepare something I didn't like broccoli. Ooh. And the rule was you had to eat everything on your plate before you're dismissed, right? So occasionally, in rare moments of maturity, I would eat the broccoli first, get it out of the way, so that I could then enjoy the rest of the meal. You see what I'm saying? Well, in light of that, we're going to do some broccoli first, okay? But stay with me, because it's going to get really cool. Okay, so we're going to have to talk about sets. We're going to have to do a little bit of math here. And you'll see a set is just a collection of elements with a common defined property. And so when we're talking about sets of numbers, a set of numbers is just numbers that have something in common with each other. And you can define sets lots of different ways. In most sets, some numbers are included and other numbers are excluded. So we're all about sets today. And for example, consider the set of even numbers. So we got some numbers there. The set of even numbers would contain those ones, and it would exclude all the others, right? Because numbers that are divisible by 2, evenly divisible by 2. We could then consider the set of negative numbers. That's a different set. The set of negative numbers is a different set, and so it will have different numbers contained within it. It'll have those ones, and it will exclude the others. And those two sets are very easy because you can tell just by looking at the number whether or not it belongs to the set, can't you? Even, well, does it end in 0, 2, 4, 6, 8? Well, yeah, it belongs. Or is it a negative number? Well, you just look and see if there's a little negative sign in front of it. It's pretty easy. We're going to talk about a set that's a little bit more complex, where you can't tell just by looking at the number whether or not it belongs. You're going to have to think about it a little bit. You can figure whether the number belongs, but not just by looking at it. And the set we're going to talk about is called the Mandelbrot set. The Mandelbrot set, named after Benoit Mandelbrot, mathematician, very famous mathematician. And it's defined by this little formula that you see there. And C is the number that you're checking to see if it belongs to the Mandelbrot set. So that's what C is. And Z is another number that, in fact, there's many different Z's. That's why it has a little subscript N next to it. So there's a first Z, a second Z, a third Z, and fourth Z. You can think of them like a sequence of mailboxes. Each one's got a number in it. And if that Z sequence gets bigger and bigger and bigger, then that means C is not part of the Mandelbrot set. Whereas if the sequence of Z stays small, then C is part of the Mandelbrot set. That sounds very complicated. It's actually very simple. And we'll do a couple, and then you'll see how intuitive it is. It's really quite simple. So there's our little formula. Z, and by the way, Zn plus 1, that means that's the next mailbox. That's the next value of Z. And so it depends on the previous value and the number C. So we're going to ask, is the number 1 part of the Mandelbrot set? So that means C equals 1, because C is the number we're checking to see if it belongs to the Mandelbrot set. So we're going to plug that in. You can see we're plugging that in for C there. So Z squared plus 1 is the next value of Z. Now, the first value of Z is always 0. That's just part of the definition. So the first value is 0. We're going to plug that in. So you have 0 squared which is 0. 0 times 0 is 0. Plus 1 is 1, yes. See, this isn't that hard. It really isn't. And so that's our new value of z. Now we're going to plug that back in like this. Now we have 1 squared, which is 1, plus 1 is 2. Very good. Even the Common Core folks are getting this. Okay. All right. We're going to put that back in. So we have now 2 squared, which is 4, plus 1 is 5. Okay. Put it back in. 5 squared is 25, plus 1 is 26. Put that back in. 26 squared. Oh, okay. Getting a little hard, isn't it? Okay. But we don't have to do any more. You can see what's happening. Is z staying small? No, it's getting big. It's getting very big very fast. So is the number 1 part of the Mandelbrot set? The answer is no. No, because the sequence of z has to stay small for c to be a member of the Mandelbrot set. So number 1 is not part of the Mandelbrot set. Let's check another one. Let's check negative 1. Is negative 1 part of the Mandelbrot set? So we're going to plug that in now. So we have z squared minus 1 is the new value of z, right? And we'll start z equals 0, and we'll plug that in. So now we have 0 squared, which is 0 minus 1 is negative 1, right? And we plug that back in. Now negative 1 squared, negative 1 times itself is positive 1. Minus 1 is 0. Well, that's kind of interesting. Put that back in. 0 squared. Wait a minute. This looks familiar. So it goes 0, negative 1, 0, negative 1. See that? Interesting. Does z stay small? Yeah. It never gets greater in absolute magnitude than 1. So is negative 1 part of the Mandelbrot set? Yes. Okay, you got it? It's easy. Tedious, but easy. Okay? So you can check any number. All you have to do is run it through that formula and take a look at what's happening with z. And sometimes it'll stay. If we tried it with 0, you'd find z is always 0. And so 0 is part of the Mandelbrot set as well. Negative 1 is part of the Mandelbrot set. Positive 1 is not. Okay, there's one more complication, and then it's going to get really cool. The Mandelbrot set also includes what are called complex and imaginary numbers. I hate the terminology because imaginary makes you think it doesn't exist. Well, they do exist. They do exist, but an imaginary number is a number that when you square it, you get a negative number. And that's a little hard for us to comprehend, right? Because and the sort of standard imaginary number is abbreviated by the lowercase I. And I squared, by definition, is negative 1. Okay? And then there are other imaginary numbers. And again, I hate the name because they do exist. And to add insult to injury, the numbers that are not imaginary are called real. But they all exist. It's just, a little bit hard for us to imagine. Imaginary numbers are not positive, right? Because a positive number squared is positive. And imaginary numbers are not negative because a negative number squared is positive. And imaginary numbers are not 0 because 0 squared is 0. So how do you have something that's not positive, not negative, and not 0? That's an imaginary number. And they do exist. It's just we're kind of uncomfortable with them because most people don't have a lot of experience with these numbers. It's kind of like when you're a little kid and you're first exposed to a negative number. You say, well, how can something be less than nothing? That doesn't make any sense, right? Then you get a little bit older, you get a bank account, suddenly negative numbers make a lot of sense, right? Yeah. Well, it's the same way with the imaginary numbers. They do exist. It's just that most of us never really use them. How do we think about a number that's not positive, not negative, and not 0? Well, one way to think about it would be to consider a number line. So you have, on the number line, you have 0 there in the middle. You have positive numbers to the right of 0. You have negative numbers to the left of 0. Where are you going to put I? How about above 0, like that? Oh, that makes sense, right? It's not positive. It's not to the right of 0. It's not negative. It's not to the left of 0, but it's also not 0. It's off axis. And so you can think of the imaginary numbers as being on a different axis than the real numbers. And that is a very common way that mathematicians will express these numbers. And you can multiply the imaginary number I, which is it's the same distance from 0 as 1. Okay, and remember I squared is negative 1. And you can multiply that imaginary number by any real number and you get all these other imaginary numbers, you see. And so that generates that axis. You can also have complex numbers. They're called complex because they have a real part and an imaginary part. And they're off axis. And by convention, the real part we plot that's their x coordinate, and the imaginary part is their y coordinate. And so this is very useful in mathematics to talk about these complex numbers, because even though it's one number, you can represent it as a point on a plane. And that's kind of neat. So you can actually make some graphs and things that way. So those are complex numbers and imaginary numbers. They're off-axis. And what we're going to do then is make a map of the Mandelbrot set, because it was kind of tedious going through that and checking that, but computers are great at doing tedious things. They can do math very quickly over and over. And what we'll do is we'll make a map of which points belong to the Mandelbrot set and which points don't. And that way, we won't have to run through that formula. We can just look at the map then and say, okay, that number, it does belong, and that number doesn't. So for example, numbers that do belong to the Mandelbrot set, we'll color those black. We checked -1, we found it did belong to the Mandelbrot set, right? Because z remains small, right? And if we checked 0, we'd find it also belongs to the Mandelbrot set. If we checked other points, we'd find that all these points belong to the Mandelbrot set as well, just as examples, had we checked them. And then for points that do not belong to the Mandelbrot set, we'll color those red. Okay, and we checked 1. Remember, we found that 1, the sequence of z got really big. And so that means it's not part of the Mandelbrot set. Had we checked some of these other numbers, we'd find that they do not belong to the Mandelbrot set as well. Now, what's fascinating is that the shape here that emerges, this map of the Mandelbrot set, turns out to be something that's not simple at all. You might think, well, it'll be a circle or something. You can tell it's not, though, even right there. But as we have the computer check more and more points, we get a complete map of the Mandelbrot set. And the map that we get looks like this. It's surprisingly complicated and rather beautiful. And so, again, what we're having here, it's just a map of which points belong. Black means they belong to the Mandelbrot set. Color means they don't. And I shaded the colors so that if the sequence of z gets really big really fast, I made it kind of a dark color. So the points that are real far away from the Mandelbrot set. Whereas if z gets big, but it does so slowly, then I colored it like a brighter color like yellow. So the points that don't belong are shaded. The points that do belong, those are all black. Just by convention, that's the way they do it. The colors are arbitrary. I could have picked any color I wanted to, except just by convention, the points that do belong are always colored black by convention. And so now I don't have to go through and run through that formula. The computer's done it for me. I can look and say, does 1/2 I belong to the Mandelbrot set? The answer is yes, it does. You can see it's black. Okay? And you can see the number 0 belongs. You can see the number 1 doesn't, and so on and so forth. And so I'm going to remove that grid, because what's interesting is this shape. It turns out this map of which points belong to the Mandelbrot set turns out to be just wonderful. It's remarkably complex and beautiful and surprising. No one was expecting this to exist in the world of math, but there it is. And it is a fascinating shape. You have sort of, there's sort of 3 types of shapes that stand out, at least to my eyes. There's the largest shape, which is called a cardioid. That's kind of that heart-shaped feature. And then growing off of that are a bunch of circles, and they are perfect circles. And then growing off of that are other circles and these little tendrils that kind of, like little lightning bolts that grow away from it. Now, the main shape, the cardioid, is what you get when you take one circle and you roll it around another circle, keeping your pencil on one point on the main circle. That's a cardioid, and you can see that is the exact shape of the main part of the Mandelbrot set. Nobody was expecting that, but there it is. And then all the other shapes are either perfect circles or these little lightning bolt wisps that kind of stem away from it. Now, if we can actually zoom in, thanks to the power of computing technology, we can zoom in on various sections of the Mandelbrot set and see what it looks like. And so we find, for example, if we zoom in on this upper tendril there, you can see that it branches off. That circle has another circle on top of it, which has another circle on top of it, and it grows into this little sort of little tree there, where it has 2 branches on it and a trunk, so 3 total. So it branches off into 3. You see that? 3 branches. And if you look at the next one to the left, it branches off into 5. Can you count that? Including the trunk, including the stem. 1, 2, 3, 4, 5. The next one is 7, 9, 11, 13, 15, 17. All of the odd numbers. Isn't that interesting? Each one has 2 more tendrils than the previous one. That's interesting. Nobody was expecting that. And if we go to the right side, we find all the numbers, evens and odds. And so 3, 4, 5, 6, 7, 8. Interesting. All the way down to infinity. And on the left side, we have all the odds all the way down to odd infinity, apparently. Interesting. And so apparently the Mandelbrot set somehow knows how to count. That's kind of fascinating. And all we're doing is looking at a map of which points belong, and yet it turns out these structures are remarkable. Not only that, but if you take 3 and the 5, and of course you add those together, you get 8, and lo and behold, that is exactly how many the one in between them has. Isn't that interesting? If you count the tendrils there, I know they're kind of small, but it's got 8 tendrils. And that is true for all of them. If you go in between any of them, the number of tendrils in between is the sum of the two surrounding them. Isn't that fascinating? So not only does the Mandelbrot set know how to count, it knows how to add. Isn't that interesting? Nobody was expecting that. Fascinating. So all that built into a map of which points belong to that simple little formula, z squared plus c. One of the most remarkable things about the Mandelbrot set, though, concerns this little spike that we have growing off the left of the set there. And you'll notice that that spike has a little black bump on the end of it. What could that be? Well, let's zoom in on that and see what that looks like, that little bump. Turns out it's another Mandelbrot set. Isn't that fascinating? And it's almost identical to the original. It's got the main cardioid, the circles growing off of it. The only difference is it's got extra spikes growing off of it. We zoomed in on a spike, and the baby version had extra spikes growing off of it. And if you'll notice, one of those spikes, the one at the very end, has a little black spot on it. What could that be? Well, let's zoom in on that. Turns out it's another one. Isn't that interesting? And it's again, identical to the original, except it's got even more spikes growing off of it because we zoomed in on a spike of a spike, and it's got extra spikes growing off of it. And it's got a little thing there too. What could that possibly be? Well, it's another one, and so on and so forth. This continues infinitely. Interesting. So the Mandelbrot set has an infinite number of baby Mandelbrot sets growing off of that spike. And each one of those has a spike, has a Mandelbrot growing off of it, and so on. All of that, just a tiny little section of the original. Look how much we've zoomed in there. It's quite amazing. Isn't that fascinating? And nobody was expecting that. Who knew that when you plotted a map of which numbers belong to z squared plus c, you would get this amazing structure? And it's not just the overall shape that repeats infinitely. If you zoom in on any part of the Mandelbrot set, it goes forever. And it's quite fascinating to see this. You might think, well, it's going to end at some point. I'm just going to keep zooming in until it stops. But it just doesn't stop. No matter what you zoom in on, it just keeps fragmenting and smaller and smaller scales. It's not like the physical universe. The physical universe eventually get down to atoms. There's no atoms here. This is made of math. Okay? And so it goes on literally forever. Isn't that fascinating? And of course, well, we'd be here all day if we zoomed in on the whole thing, right? Because we would literally take forever. But it's quite fascinating. One of the interesting regions in which we can zoom in on the Mandelbrot set is the valley between the main cardioid and the first disc, that big circle that's growing off to the left of the cardioid. That valley, if we zoom in on it, either the top or the bottom, they're symmetric. If we zoom in on that, it's called the Valley of the Seahorses. And you can see it looks like seahorses off to the right. They're upside down. And double spirals off to the left. So we can zoom in on those shapes and see what they look like. So let's zoom in on one of those seahorses and see what that looks like here. And by the way, the colors are arbitrary, so we'll change those every now and then just to keep things interesting. But bright colors mean close to the Mandelbrot set, but not quite on it. Dark colors mean far away from the Mandelbrot set, and black means it's on the Mandelbrot set. So we zoom in on one of these seahorses. Now, keep in mind, all you're looking at is the plot of an equation. It's the equation z squared plus c, and which points belong to that. And what you have, given that seahorse is very brightly colored, that means that those points are very close to being on the Mandelbrot set, which means there must be actually a very thin black thread that extends away from that circle that wiggles around it's incredibly wiggly. In fact, it's infinitely wiggly, if that makes any sense. It's as wiggly as possible for 2 dimensions. And it wiggles around, and what you're seeing there is the black is too thin for the computer to plot it. But the fact that you're seeing bright blue there indicates that those points are very close to being on the Mandelbrot set. So that seahorse is made of an infinitely wiggly thread, or multiple threads, that wrap around and form kind of a spider web structure there in the middle. Quite beautiful, and they form a beautiful spiral up near the top. Isn't that stunning? And who would have expected that such beauty would be built into a map of the Mandelbrot set? It's absolutely fascinating. So let's zoom in a little bit more and see what that spiderweb structure looks like. And it looks like that. And I found from experience you can zoom in on the center of that to your heart's content and nothing changes. It goes forever. It's an infinite spiderweb. And so what we'll do is we'll go off axis. We'll look at one of the strands of the spiderweb, see what it's made of. And we find the spiderweb strand is made of more spiderweb strands, interestingly, and spirals as well. Quite lovely, really, very beautiful. We zoom in on one of those. We find an interesting structure there. You find that there's kind of two central hubs, one on the top, one on the bottom, right? You see those where there's bright yellow in this illustration. And then it goes to 4 in the middle there. You can see there's 4. And then when we zoom in, you'll see it'll go to 8, 16, 32, 64. It's all the powers of 2. So not only does the Mandelbrot set know how to count, know how to add, it knows how to do powers of 2, interestingly. So let's zoom in on this central, that central 4 little square structure there. And you find that in the middle is, well, that's interesting. It goes from 4 to 8 to 16, and then right in the middle is, of course, another baby version of the Mandelbrot set. Isn't that amazing? And we've zoomed in, I don't know how many times, but this is a tiny little structure built into the original. And you can see that it, too, has a little baby Mandelbrot set on its spike, just like the original did. But now it's surrounded by all this extra stuff, all this extra kind of spiderweb type structure, because we zoomed in on a spiderweb, and the baby version apparently inherits the properties of the section of the parent that it grows off of. So quite stunning. And take a look at how small this is compared to the original when we zoom back out. It's quite amazing. And that just gives you a little window into the mind of God. Because if you think about it, God is responsible for numbers. God is the reason that numbers exist, because they exist in his mind. And we'll talk about this more later. But what this is it's giving you a little window into how God thinks. And so when you zoom in on these things and you think, wow, God is infinite, this is just a little taste of what infinity is like. Just a taste of it. We can't really experience infinity in its fullness. We can get a glimpse of it. Well, let's go back to the Valley of the Seahorses. They're on the right side. And this time we'll go off to the left in what they call the Valley of the Double Spirals. And this is my favorite section of the Mandelbrot set. It's strikingly beautiful. It reminds me of spiral galaxies, actually, in terms of the way these structures are. It is a double spiral meaning that there are 2 strands that wrap around each other. If you were to take a look at this strand is the same as that strand, but not that one, right? Because if you follow it around, you can see, yeah, there's 2 independent strands that wrap around each other. So it's a double spiral. And it's strikingly beautiful, I think. So again, you're just seeing a map of which points belong. There must be a very thin thread of points that belong to the Mandelbrot set that wiggles around and forms this beautiful, intricate spiral structure, all built into numbers. It's been there since creation, but it was only in the 1980s that computers were fast enough to be able to plot these things in a reasonable amount of time. And it's even easier today because computers are faster. Again, I found if you zoom in on the center of that double spiral, you can do that forever. It continues infinitely. It spirals forever, literally. Infinitely smaller. So let's go off axis and zoom in on one of these strands. And quite lovely. We find that you find more double spirals off to the side, up on the top, for example. There's some of those spiderweb structures, and there's a structure, I call it a bow tie. It looks like a little bow tie there in the middle, where you have 2 double spirals that intersect in the middle. And I find these to be stunningly beautiful. So who could have guessed that this is all built into numbers? Been waiting for us to discover it for 6,000 years. And so again, you have the 2 double spirals, and then in the middle it goes to 4, 8, 16, 32. And of course, when you zoom in on the middle there, you find, lo and behold, another baby Mandelbrot set. Do you get the feeling that God really likes that shape? Because it just occurs everywhere. There's an infinite number of them. And again, it's identical to the original, except, of course, it's rotated around. Have you noticed this one's backwards compared to the original? Because we zoomed in on a spiral, and so it got rotated around. And also, we have double spirals growing off of it. And you can see the 8 primary ones there, and then there's 16 inside that, and 32 inside that. All the powers of 2, all the way up to infinity, amazingly. And of course, it's got a little baby on its spike as well, as they all do. So not only does the Mandelbrot contain an infinite number of copies of itself, but each of those copies has an infinite number of copies as well. Because if you think about it, this also has a Valley of Seahorses, doesn't it? I could zoom in on it, and so on. So it just gives you a little glimpse into the infinite mind of God. One other valley that's interesting to zoom in on is the one on the where the cardioid, the main cusp of the cardioid, and we call this the Valley of the Elephants, and you'll see why when we zoom in here. Mathematicians like to give names to these different sections, and Valley of the Elephants. It looks like elephants marching one after the next, doesn't it? And their mirror image as if they're hanging from the ceiling, going along that way. But we'll go to the bottom row. It reminded me of elephants in a circus. They're like standing on a ball, right? Because each one of those circles has one elephant growing off of it, doesn't it? And there's an infinite number of them. They go all the way to infinity into that cusp. So each circle, one elephant balancing on it, as if a circus elephant. We can zoom in on the trunk of one of these elephants, and you can see the trunk wraps infinitely, actually. It wraps around itself, and it's quite lovely. And again, you can zoom in on the center of that forever. It continues infinitely, gets smaller and smaller to an infinitesimal scale. So we'll go off axis and look at the structure on the side. We find, again, it looks like kind of elephant-like structures. There's some bow ties there, too, if we zoom in on one of those. There's one of those bow tie shapes, but now they're single spirals. Yeah, this is an Alienware. It's not supposed to do that. Oh, okay, we're all right. Okay. The reason I got this is so I could do this presentation. All right. No, it's working great. So again, you have that bow tie structure, but it's single spirals rather than double. And if you zoom in on the center, it goes from 2. It's doing it again. That's weird. Let me back up a little bit. Yeah, I don't know why it's not animating. I'm sorry about that. But anyway, that's what you get to when you get to the center. And you get this beautiful baby Mandelbrot that's surrounded by all this lovely structure. Isn't that stunning? And all built into this shape. It's just a plot of which numbers belong to the Mandelbrot set, z squared plus c. Seems very simple, and yet God has built incredible beauty into math. That's remarkable. All that, just a map of that formula, which numbers c remain, for which the sequence of z remains small. That's all there is to it. And so that got me thinking, what happens if we explore other formulas? I mean, this shape itself, you understand, you could spend the rest of your life studying this and you would only scratch the surface because it's infinitely complex. And it's just one equation. That tells us something about the mind of God. I found that if I change c, if I make it like half c or 2c or minus c, all it does is change the shape. It'll flip it around or make it bigger or smaller. You still get the Mandelbrot set. What if I change z squared, though, to something else? What if I try z cubed? What do I get? Well, it turns out you get a different shape. Now we've got another object to study. And is it complex like the Mandelbrot? Well, let's find out. Let's take a look at this shape. They call this a multibrot because it's a multiple of the Mandelbrot set. And so this is z cubed plus c. Those are the points in black, are the points that belong to that formula when you run it through that iteration. And you notice what's happened here. Everything's gone up by 1. Because remember, the Mandelbrot set had the cardioid, which has 1 cusp, and the rest of it's round. Now the main shape has 2 cusps, one on the left, one on the right. And the Mandelbrot set had perfect circles growing on them, which have no cusps, and now they have cardioids growing off of them, which have 1 cusp. Everything's gone up by 1. The main shape there, with the 2 lobes, that's called a nephroid, and that's what happens when you take a circle that's half the size of the other one and you roll it around like that. That's a nephroid. And you can see that is exactly the shape that is produced when we have z cubed plus c. Why? Nobody knows. I'm sure there's a reason, a very good mathematical reason. We have yet to discover it. Because our ability to think God's thoughts after him is quite limited. And in fact, you can see how the Mandelbrot changes into the multibrot. What I did was I ran it through the formula and I changed it gradually. I changed it from z squared to z 2.1, 2.2, 2.3, all the way up to z cubed. And so you can see what happens. You can see how everything gets kind of doubled. Some things get up by a factor of 4, like the little baby Mandelbrot there. It first gets split into 2, and then it's joined by a twin, so it actually ends up being 4. But most things are doubled. And so that's kind of interesting. Now, the one thing that doesn't really change very much, in fact, let me back up and do that again. The one thing that doesn't change very much is the Valley of the Elephants, right? Everything else gets kind of moved around, but this valley looks like it stays pretty constant. So I thought, what would happen then if we zoomed in? Does this shape also have a Valley of the Elephants? Well, let's find out. Let's zoom in on it. See what we find. Lo and behold, we find elephants. How about that? But you notice before we had circles and we had one elephant growing off of each circle. Now we have cardioids, and there's 2 elephants growing off of each one. So the elephants have doubled. Before we had an infinite number of elephants, and now we have twice that many. Simmer on that for a while. So there you go. Each cardioid now has 2 elephants growing off of it. Isn't that amazing? So, and we can zoom in on the trunk of one of these elephants and see what happens. You're going to get the bow tie structures, you think? Let's find out. The bow ties have become 3. They've gained a spiral, right? Instead of just 2 spirals intersecting, they have 3 now. And lo and behold, what do you find in the center there? First of all, it goes from 3 to 9 to 27 and so on. It's all the powers of 3 now instead of the powers of 2. And you zoom in on the center one, and sure enough, you get the basic shape. You get the nephroid with the cardioids growing off of it. So it's a fractal as well. Anything like this that repeats infinitely is called a fractal. A fractal is something where the overall shape is repeated on smaller and smaller scales. And so we've just explored 2 different fractals now. Kind of amazing. So that's what happens when you have z cubed plus c. What happens if you do z to the 4th? Well, you get that. Everything goes up when you have one other cusp now, you see. And z to the 5th. Z to the 5th gives you a 4, if I back up a second, z to the 4th gives you kind of a 3-fold symmetry. Z to the 5th gives you a 4-fold symmetry. Z to the 6th gives you a 5-fold symmetry. And so it occurred to me if I made z to the 7th, I could get snowflakes. 6-fold symmetry. And when you zoom in on this, do you get snowflakes? Absolutely. You zoom in on portions of it, you get these beautiful snowflake structures. So it's also fractal. Isn't that fascinating? I also tried negative powers. What happens when you try z to the negative 2? Now, the interesting thing about this, remember, black are points that do belong, and colored are points that don't. And so what happens is now almost the entire universe belongs. The black is outside now. It's inverted because it's a negative power, you see. And so now most of the universe belongs to that set. It's these points in the middle that don't. And if I zoom in on these are fascinating because it produces kind of like a pebble-like structure that I think are remarkably beautiful. Isn't that interesting? And if we zoom in on that, what do we find? Pebbles upon pebbles of stunning beauty. Does it repeat infinitely? Well, let's zoom in here. Absolutely. It goes on forever and ever and ever with the pebbles of smaller and smaller scales. It's not like the physical universe where you get down to atoms and then they're just spheres. Here, it goes on literally forever. You could zoom in on that for the rest of your life. So that's z to the negative 2. What happens if you do z to the negative 3? You get that. Z to the negative 4, you get that. Z to the negative 5. Again, there's a progression there. And so there's another type of snowflake that you can get. So isn't that fascinating? All we're doing is looking at maps of which points belong to that little formula, and changing the formula doesn't just gives you new shapes. So what does all this mean? I mean, are we just looking at pretty shapes here? What does all it mean? Well, my question is, what causes this beauty in fractals? Where does it come from? How do we account for it? How do we make sense of it? What causes the complexity in fractals? The fact that you can zoom in on them, they have these mathematical properties, they continue infinitely. How do we make sense of that? Well, first of all, what causes the beauty in fractals? Is it the man-made color scheme? I picked the colors. I think they're pretty. But the fact is, even if you take away the color, the shape is still beautiful, even in grayscale. Okay, and I didn't pick the shape. Nobody did. No human did. So it's not the man-made color scheme. That's not it. I think that adds to it, the way a little bit of salt will bring out the flavor of your food. But it's not creating the beauty, not at all. Did the computer create the beauty? Well, we saw the computer plot this, but the fact is, the computer just did quickly what you could do manually. We did the first 2 points manually. Remember, we did -1 and -1, and we found whether or not they belong. So no, this shape is built into numbers. The computer just helped us to reveal it quickly. You could theoretically do this all by hand. It would just take forever. And so this didn't create the beauty any more than a microscope creates the complexity of a microbe. No, it just allows us to see it. Did people make this? Well, we came up with the formula, but what we've seen is that the formula doesn't really matter too much. You can change the formula, you still get these wonderful shapes. And frankly, no human being sat down and said, okay, I think I'm going to make this shape where it's a cardioid here, and then I'm going to put some circles on it, and I think I'll draw an infinite number of, well, human beings can't draw an infinite number of things. Human beings did not create this. We can't create infinite. We discovered it. We did not create it. And so it seems to me the beauty is built into math. The beauty of fractals is built into math somehow. Well, what causes the complexity in fractals? The fact that they repeat and have these mathematical properties, what accounts for that? Did the computer create it? Obviously not. The computer simply reveals it. You could do these, you could plot these manually, theoretically. Did human beings create it? We can't create things that are infinitely complex. Think about it. Man-made machines, you get down to some level and then they're very crude and simple. We can't do that. We can't create an infinite number of minis built into the original. We could create several, but not an infinite number. That's beyond us. It's not something that human beings created. Did the formula create it? Well, the formula doesn't matter too much. The formula reveals it. The formula defines what points belong and what not. But it's not like people picked a formula to give that shape. People picked the formula and were surprised by that shape. Very surprised. So it seems to me the complexity is somehow built into math. Interesting. Here we have a shape that's been built into numbers, built into math. What is math? Aside from that subject that's really hard in school, math is the study of the relationship between numbers. That's really how you could define it. It's how numbers relate to each other. Well, what are numbers then? And it's funny, some of these things that we use every day and we don't think about how are they defined? How would you define a number? I looked through several dictionaries, and it's hard to get an exact definition of that. The best I could find is a dictionary that said numbers are a concept of quantity. I think that's the best definition I've been able to see. And so if you have 2 oranges and 2 rocks and 2 people and 2 galaxies, what do they all have in common? Two-ness. You abstract away the physical thing, and what you're left with is a concept, the concept of quantity. That's what numbers are. They are a concept. Now, the thing about concepts is they exist in the mind. Concepts are something you think. Numbers are something you think. They are abstract in nature, not physical. You cannot stub your toe on the number 2. You can stub your toe on something physical that maybe there's 2 of them, but you can't stub your toe on two-ness, right? You just can't do that because it's not physical. They exist in the mind. You can't trip over a law of mathematics or pull one out of the refrigerator or accidentally swallow one. They're non-physical. They are abstract. They exist in the mind. You say, well, I don't know, that number 3 is physical, right? I see it there on the screen. That's the number 3. Is it the number 3, really? Because if so, then I just destroyed the number 3. Oh, wait a minute. That wasn't actually 3, right? Because it's not like children will now have to count 1, 2, 4, because there's no more 3. I just destroyed it. No. We get it. That was a representation of 3, right? That was a numeral. Written numerals are not numbers. They are representations of numbers, and they can be written different ways. I could write 3 with 3 vertical lines, right, like they do in Roman numerals, or I could use, Arabic or whatever. Those are just representations of numbers. But the concept of 3-ness is not something you can write down because it's mental. It exists in the mind. Laws of math are conceptual. They exist in the mind. So these laws that we have, the multiplication, the commutative property of multiplication or distributive property and so on, these are conceptual. They exist in the mind. Now, they're very effective in how we get along in the universe. They help us, but they exist in the mind. So where do laws of math come from then? There's an interesting question. We use these laws of math, the Pythagorean theorem and so on. We use these laws. Where do they come from? Did laws of math evolve? Well, I mean, we've seen a shape that's incredibly complex and beautiful. And in the natural world, in the physical world, when we find something like that, an organism that's incredibly complex and appears well-designed, the secularists say, well, that evolved, right? It used to be very simple, but then it gradually became more complex over time. Is that going to work for math? It doesn't really work for biology, but was it like the Pythagorean theorem didn't used to be true, but it gradually Well, no. The 2 plus 2 used to equal 3, but then it slowly changed, and now it equals 4. And no, laws of math don't evolve, do they? They've always been exactly as they are now. That we discovered them over time, but it's not like 2 plus 2 ever, at one point in time, equaled something other than 4. They've always been the way they are now. There's no such thing as evolutionary math. Everybody does math like a creationist. Isn't that interesting? Whether they profess it or not. Were they created by people? Oh, well, Pythagoras created the Pythagorean theorem. Really? Did triangles not add up that way before Pythagoras? Well, he just discovered it. He wasn't the first, by the way, but he was able to demonstrate that. It's very clever. They're not created by people. Laws of math worked perfectly well before people were around to describe them. The way the planets orbit the sun, they obey what are called Kepler's laws, and those are mathematical. The period of a planet squared is equal to its distance from the sun cubed in the appropriate units. And so, now, was that the case before people? Yeah. A few days before people. Because planets are made on day 4, people are made on day 6. Yeah, but my point is the planets orbited perfectly fine before people came along, and they orbited according to laws of mathematics. And even the secularists would concede that. So my point is people did not create laws of math because math worked perfectly well before people were around to describe it. Did they come from the universe? That's a common belief, especially among secularists, is that, well, the universe behaves a certain way, and we call that math. But I think that is utterly indefensible because there are things in mathematics that have no analogy in the physical universe. For example, the number of dimensions. The physical universe has 3 dimensions of space, 1 of time. In math, you can have any number of dimensions. You can have 16 dimensions if you like. There's a thing called Hilbert space that has infinite number of dimensions. That has no correspondence to anything in the physical universe. And yet, it makes sense. There's rationality to it. So my point is math goes beyond the physical universe. The physical universe doesn't get infinitely small. You get down to the level of atoms and then in quarks, and then there's kind of a quantum fuzziness there. But these shapes go on forever. So math didn't come from the universe. Now, it's interesting that math can describe the universe, but that's a separate question. That's a separate puzzle for secularists. Obviously, math doesn't come from the universe because it goes beyond the universe. You can do things in math you can't do in the physical universe. You can have infinities in math. You can't have those in the physical universe in terms of infinite lengths and things like that. Seems to me that laws of math stem from the mind of God. In the Christian worldview, I can make sense of numbers. Numbers are what God thinks of quantities, which is how they exist before people, you see. And laws of math, they stem from the mind of God. Mathematics is the way God thinks about numbers. That's what math is. And if you want to study it right, you need to know something about God. Laws of mathematics are conceptual. They exist in the mind. They're universal, meaning they apply everywhere, right? It's not like 2 plus 2 equals 4. Well, sure, here on Earth, but on the moon it might equal 5 or 7. No, they apply everywhere, don't they? They're invariant, meaning they don't change with time. 2 plus 2 equals 4 today and tomorrow and last week and next Thursday. It doesn't matter, right? And we all assume that. And they're exceptionless. It's not like 2 plus 2 equals 4 most of the time, but every now and then it's 7. No, it doesn't work that way, does it? And if you think about it, these properties of laws of mathematics make sense in light of the fact that laws of mathematics stem from the mind of God. Because God's thoughts are conceptual, because all thoughts are conceptual. So naturally, laws of mathematics would be conceptual. They would be universal because God is omnipresent. He is sovereign over all creation. He's everywhere. And so his thinking will govern correct thinking everywhere in the universe. God does not change with time. Therefore, laws of mathematics will not change with time. The way God thinks about numbers today is the way he thought about numbers yesterday and the way he will always think about numbers because God does not change. And laws of mathematics have no exceptions because God is sovereign over everything. And so they cannot defy their creator that way. They can't. And so I would argue that the Christian worldview can make sense of fractals. We can make sense that mathematics has beauty built into it and complexity built into it. We can make sense of laws of mathematics and the reason that they are universal and invariant and exceptionless. That all stems from the nature of God. The Christian worldview can account for this. The naturalist has a problem. Somebody who believes that nature's all that there is. He's got a problem because on the one hand, laws of mathematics are conceptual. They exist in the mind. You can't stub your toe on a law of math. Accidentally swallow one. You can't do that. They're non-physical. On the other hand, laws of mathematics existed before people. So on the one hand, they're a product of the mind. On the other hand, they existed before human minds. But you see, in the secular view, human minds are the first, unless there's aliens or something out there, right? And even then, the mathematics would exist before them, because the universe is governed by mathematical laws. And so the naturalist has a real problem on his hands. He's got to account for laws of math that are conceptual, and yet he doesn't have a mind beyond people to appeal to. That's a problem. But in the Christian worldview, it makes perfect sense, because we understand there's a mind beyond people, the mind of God, that is sovereign over the entire universe. I can make sense of laws of mathematics and their properties. The secularists can't. There are also physical fractals. This is kind of interesting. Now, the perfect fractals we've discussed that repeat infinitely, those are only found in mathematics. Mathematics goes on forever. The physical world, you zoom in so much and you get to the level of atoms and things stop being fractal. But nonetheless, the physical world contains things that are approximate fractals. They repeat many times, just not infinitely times. Okay? And so let's take a look at some of these. Fractals in the physical world. One that you're very familiar with in Nebraska, the snowflake. Yeah. And these little gems from heaven that we get angry at and shovel them off our car, but they're quite stunningly beautiful when you take a look at them on the microscopic scale. They are fractal in the sense that that same basic pattern repeats. Maybe not exactly, but you can zoom in, you still get the six-fold symmetry due to the nature of the water molecule and so on. So snow has a fractal shape to it. It really does. That stuff that grows on your windows. I always thought this was amazing when I was a kid, and frankly, I still think it's amazing. These beautiful patterns that will form on your window when the humidity is right and the temperature's right. It's a fractal pattern. You zoom in on it, it branches and it branches and it branches and so on. And so and it's quite lovely. And ferns are fractal because you have a stem and it has growing off the side stems, which have growing off the sides of those stems, which have growing off the side, and so on. And it repeats on smaller and smaller scales. The overall fern looks similar to any section of it. That is a fractal. I even found fractal broccoli, so I guess broccoli is good for something after all. So there you go. It's called Romanesco broccoli. And you zoom in on it, you see it's these cone shapes, but the cones are made of smaller cones, which are made of smaller cones, which are made of smaller cones. And so that is a fractal, interestingly. So the way coastlines are, the way they divide, the way the rivers branch and branch into branches and branch into branches of branches, the way the coastline is fractal. Mountaintops, the way they split is fractal, the way they branch into branches and so on. Clouds have a fractal nature to them. Am I looking at the entire sky? Am I zoomed in on one very small part of the sky? Hard to tell, because the same kind of patterns repeat on smaller and smaller scales. The way lightning branches is fractal, because you have the main bolt and it branches into smaller bolts, which branch into smaller bolts, and so on. And so lightning does have that fractal property to it. And you can actually see it, I think this is wonderful, in time-lapse or slow motion, where you can see it, and isn't that amazing, until the leader finally connects, and then most of the current goes down that path. But the way it branches is fractal. So here's my question then. Why do fractals occur both in math and in the physical world? Right? Because we got mathematical fractals that have been built into math since creation, only discovered in the 1980s. And then we've got these physical fractals that people have known about for a long time that are approximate fractals, lightning bolts and mountain chains and so on. Why do they exist together? I mean, that's a mathematical plot. That doesn't exist physically anywhere in the world. That's a multibrot. It's z to the 7th plus c. And yet, that does exist in the physical world. We've got a lot of them outside right now. This is part of the Mandelbrot set. It's one of those tendril branches, and yet that is a lightning bolt that exists physically. So one is math. It's not made of atoms. It exists in the mind. The other is physical. It's made of atoms. It exists in the physical universe. We have this shape. That's actually a mathematical graph. It's called a Barnsley fern. And what it is each leaf of the fern is the entire fern. I'll show you this. Watch this. The entire fern is one of its leaves. See that? That's just cool. Let's do that again. You can do it infinitely, right? So that's a Barnsley fern. And yet there are real ferns that approximate that. Now, they don't go on forever, right? Because at some point you get down to atoms, and even before that, the fractal breaks down. But they're similar. One exists only in the conceptual world of math, the other, physical. You got that shape? That's a mathematical plot, and yet that grows on your windows. You've got this shape, that's a mathematical plot. It does not exist in the physical world, whereas this, unfortunately, does. You got this shape, that's part of the Mandelbrot set, part of the Valley of the Double Spirals. You can't see that anywhere in the physical universe, or stub your toe on it, or touch it, but this you can see in your telescope. Not too far off the Big Dipper, the handle of the Big Dipper. Yeah, I've seen it many times. Interesting. So why do fractals occur both in math and the physical world? Now, one answer to this, and I think it's a reasonable answer, it's just insufficient, is that the physical universe obeys mathematical laws. The universe obeys math. So it stands to reason that if fractals can occur in math, they could also occur in the physical world, since the physical world obeys math. I agree, that's good. But then, of course, I'm going to have to ask, why does the physical universe obey mathematical laws? Well, we just take that for granted. Yeah, we do. But why is that? Why is it that the universe, which is physical, made up of material, obeys laws that are conceptual, that exist in the mind? How is that possible? Well, in the Christian worldview, it makes sense, because mathematics is a reflection of the way God thinks, and whose mind is in control of the universe? God's. And so naturally, mathematics will be reflected in the way the physical universe behaves. It makes sense. The universe is upheld by the mind of God. God upholds all things by the word of his power. And so the way God controls the universe will be mathematical because God thinks mathematically. So yes, the universe will obey math. But I would argue that the secular worldview can't answer that.
Human behavior.
What's that?
Human behavior.
Human behavior?
How does it fit this? Does it? Can it? Part of the mind of God.
Well, God does control us, but he's given us freedom of choice. So we're free to sin, right? And the physical universe doesn't have that option. The physical universe has no option but to obey God. But it is fallen. That's true. But nonetheless, it still obeys him perfectly. God cursed it, and it was cursed according to the way that he intended. So yeah, I think we can make sense of human behavior in the Christian worldview, because in our worldview, the physical universe is not the whole ball of wax. There's more to reality than the physical universe. There's the spiritual world as well. And in terms of the way our spirit interacts with the physical world, it's called the mind-body problem. That's an interesting issue. I'm not going to get into that, except to say that in the Christian worldview, we can make sense of the fact that we have a mind. There's something beyond, there's something more to us than simply our atoms. Isn't that right? We have a spirit. And so in the Christian worldview, the physical universe is not the only thing. There's more to reality than the physical universe. There's God as well. But I'm going to argue that the secular worldview can't make sense of why the physical universe obeys mathematical laws. Why frankly, why the laws of mathematics have the properties that they do. Why is it that laws of math are universal? And frankly, how could you possibly know that? How do you know that laws of mathematics work in the Andromeda Galaxy? You've never been there, and yet we all assume that. Every astronomer I've ever met assumes that the laws of math work the same in the distant universe as it does here. And I would argue it makes sense in the Christian worldview, because God's sovereign over the Andromeda Galaxy just as he's sovereign over the earth. And so that makes sense. Why is the universe compelled to obey math? Well, in the Christian worldview, it's because the universe is controlled by the mind of God, and God thinks mathematically. Yeah. But in the secular worldview, there's no explanation for this. You don't believe me? Dr. Eugene Wigner, who is a brilliant physicist, I believe he's a Nobel Prize winner, wrote a wonderful article entitled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences," in which he attempts to answer this question: why is it that the physical universe obeys these conceptual mathematical laws? Why is that? And it's a wonderful read. And by the way, I'm not making fun of this guy. He is brilliant. He really is. But my point is, he's not thinking as a Christian. And so what does he come up with? He says, well, it's difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and the human mind's capacity to divine them. He says it's weird enough, it's miraculous enough that there are laws of nature that are expressed mathematically. And what's even more strange is that the human mind, which I suppose in his view is just a chemical accident, has the ability to discover those laws of nature. And they're congenial to our understanding. And some of them are very simple, like F equals ma. Well, that's nice and convenient, isn't it? I mean, God couldn't have made that simpler. E equals mc squared. Why squared rather than 2.73651? Squared. It's perfect too. It's as if the universe was made to be understood, at least partly. And he says it's difficult to avoid the impression that two miracles confront us here. The existence of laws of nature, which are mathematical in nature, and the human mind's, the ability of the human mind to extract some of those, to discover those. So what is his conclusion? What does he come up with? Here's his conclusion. The miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. Isn't that interesting? And I have great respect for him for admitting that in the secular worldview, he cannot account for why there are laws of mathematics, why they exist, and why the universe obeys them, and frankly, why the human mind is able to extract them and understand them. So, and I agree that there is no solution in the secular worldview. But in the Christian worldview, it makes perfect sense, doesn't it? Because we have a mind that is sovereign over all nature. It's sovereign over concepts like mathematics, and it's sovereign over the physical universe as well. And that's the mind of God. So I can account for the success of science in my worldview. I can account for fractals. That's not to say that I understand everything about them. I don't. They're infinite. But I have a worldview in which they can exist, and it makes sense that we can have things like fractals. So we've seen that beauty, tremendous beauty of infinite complexity is built into numbers. Amazing. Revealed when we plot them by these little formulas. Numbers, we've seen, are abstract conceptions of quantity. They exist in the mind. And so when we study these fractals, we're studying the way God thinks, or at least one aspect of the way God thinks. And we get these little glimpses into infinity. You're like, wow, God's mind is awesome. Concepts require a mind. And so when you're studying numbers, you're studying the way somebody thinks about something. And of course, we've seen that numbers exist before people, and therefore they're a reflection of the way God thinks. And not always the way we think. We can make mistakes in math, God cannot. The secular worldview cannot account for the existence and properties of numbers or mathematical truths, and we've seen how that fleshes out, and we've seen that admitted by a brilliant physicist. Numbers existed before people, yet they are conceptions, meaning they require a mind, and that implies that there's a mind before people. Laws of mathematics are universal, same everywhere. Invariant, they don't change with time. They're abstract, they're not physical, and all those things make sense if laws of mathematics are the way God thinks about numbers. And so we can explain that because God himself is omnipresent and he doesn't change with time. And he is, of course, his thinking is abstract. He himself is non-material. So, of course, we can have non-material things that exist in the Christian worldview. The physical world contains fractals as well, at least approximate fractals, and we can make sense of that. But the secular worldview can't. Because why the physical universe obeys mathematical laws, according to Dr. Wigner, it's a miracle that we neither understand nor deserve. But in the Christian worldview, we can make sense of that because the universe is controlled by the mind of God. The Bible says, God himself says in Isaiah, I will accomplish all my good pleasure. God upholds all things by the word of his power. And so he does control the universe. And so, again, check us out, Biblical Science Institute. Pick up some of the resources if you can. And I'll see you back this afternoon for the Q&A session. Thank you very much. Okay, well, it's good to be back with you this morning, and I want to talk about how science confirms biblical creation because as we proclaim the gospel, there are objections to that, right? People say, no, you can't trust the Bible because, and probably the number one answer is, well, science has disproved the Bible, especially in Genesis. That's where people say, maybe later on, the Exodus, that might have happened, maybe, but there's no way God created in 6 days, And because we know evolution, millions of years of evolution is the way that life came about. And so I find it very helpful to know a bit about the basics of science, just so you can talk intelligently on this subject. And I don't use these lines of evidence as a proof of creation, because we saw, if you were able to come last night, we saw that there is an ultimate proof of creation, and the fact that science is even possible is a proof of creation. But nonetheless, I think science is confirmatory. It confirms biblical creation. It's what we'd expect. If the Bible's true, we would expect science to be the way that it is. And in my career, I've had the opportunity to work with some brilliant people, truly brilliant people. And I've met a lot of very brilliant creationists. I've met the inventor of the MRI, who's a creationist, by the way, and a brilliant guy. I've met all kinds of brilliant scholars. I know a PhD from Harvard who's a brilliant creationist. He's a friend of mine. And I've met brilliant people who are on the side of evolution. In my career at the University of Colorado, when I was getting my PhD there, most of the people there were evolutionists, and they believed in the Big Bang and the billions of years, and yet they're highly intelligent. There's a tendency sometimes for us to think, well, if you don't believe the way that I do, then, well, you're just not that bright. But the fact is, there are bright people on both sides of this issue. And we saw last night the reason why that is. It's because we have a different way of looking at the world. And when I look at the world, I see it through biblical lens, and I think that that's the right way to look at it. We saw last night that biblical presuppositions are the only presuppositions that'll make knowledge possible. If you want to trade those in for something else, you're reduced to foolishness. Nonetheless, many people look at the world through the lens of secular thinking, and when you do that, you're thinking in terms of natural processes generating everything. Uniformitarianism, the idea that rates and conditions are basically the same now as they always have been, and therefore slow, gradual processes produce Earth's features. And when you look at the evidence, then you're going to tend to draw interpretations that are consistent with that belief system that you bring to the evidence. Whereas I look at the evidence through the lens of Scripture, biblical history. What we summarize, we call them the 7 C's of history, 7 words that start with C, that just kind of summarize biblical history. Creation, God created a perfect world, a world that he himself called very good. And God has high standards. If our righteousness is like filthy rags, when God looks at the world and it's very good, you can believe it's very good. It's not going to be full of the death and suffering that we have today. That was introduced, step 2 there, corruption, because God gave Adam dominion over the world. And so when Adam sinned, it affected the world, because that's the nature of authority. That's how it works. Catastrophe, the wickedness of mankind became great, and God judged the world because he's a righteous judge, and he won't tolerate sin indefinitely. He's merciful. He's willing to pay for our sin. That's awesome. But nonetheless, for those who are unrepentant, God will judge them, and he did that with water. He's going to do it again by fire. Confusion, the confusion of tongues at the Tower of Babel, where God split up the people groups into the different basic language units that we have today. Of course, languages have diversified some since. That's just natural. And then we have Christ. God himself steps into history, becomes a man, and then takes our place on the cross. That's awesome, so that we can be saved. And then the 7th C has yet to happen, at least in its fullness, the consummation, where paradise lost will be paradise restored. And we can be a part of that new earth, that new paradise, but only if our sins are forgiven. Otherwise, we'd ruin it the same way we ruined the original. And so it makes sense. And when I look at the world, I'm thinking in terms of that history, and it is recorded history, by the way. A lot of people think somehow that it's logical to just reject recorded history and then rely instead on guesswork. That's what evolutionists are doing. They're rejecting recorded history and relying on guesswork instead. And I don't find that to be particularly logical. In any case, when we look at the universe through the lens of Scripture, we're going to find that it makes sense. And I want to hit 3 areas of science where it's helpful to know just the basics. And those 3 areas would be genetics, which is the study of how traits are passed on from one organism to the next. Information theory, the idea of how information is transmitted and its source and so on. And then finally, geology, the study of rocks, and also paleontology, the fossils that we find within those rock layers. And so let's begin by jumping in to heredity, the study of how animals change over time, or how they inherit traits from their parents and so on. Do animals change over time? Let's think about dogs, for example. Do dogs change? Yeah, they change. What do they change into? Dogs, yeah. Dogs change into dogs, that's right. And that's not evolution, that's just dogs, right? And we'd expect that because the Bible tells us in Genesis 1 many times that God created animals after their kinds, or after its kind, and plants as well, after their kind, after its kind. A phrase that's used 10 times in Genesis 1, we better take it seriously. And kind would appear to be the reproductive limit of an organism. We know that because when God brought the animals to the ark, he brought 2 of each kind to preserve life. So that must be the reproductive limit of organisms. And so, by the way, kind is not the same as species. That's important because you can get different species. There is a process called speciation where you can get multiple species from a common ancestor. That happens. But they're still the same kind. A group of mosquitoes goes off and lives in a cave for 100 years, and when it's brought back out, it can't interbreed with other mosquitoes, and so it's classified as a new species. But they're still mosquitoes. What were they? Mosquitoes. What are they now? Mosquitoes. What will they always be? Mosquitoes. Yeah, that's not evolution, that's just mosquitoes. Yeah. And it's the same with dogs, and it's the same with all organisms. You can get different species, but they always remain the same kind. And God has built in that ability to diversify into organisms. You see, I find a lot of times evolutionists will misrepresent what it is that creationists teach. And they'll say, well, creationists believe that God created all the species on the earth as they are today. And in some versions, even in the locations that they are today. That is not biblical, folks. That is not what we believe. Animals do change. I don't believe that animals have always been exactly as they are today. I don't believe that there were poodles in the Garden of Eden, right? Because it was a paradise. It was very good. You're not going to have poodles in there. So, not at all. This is what we actually believe, okay? Yes, there are kinds, and yes, they diversify and they split, and the poodles are just one of those little offshoots that we see up there, ultimately as a result of sin, as we'll see. But in any case, they remain the same kinds, right? So dogs have always been dogs, always will be dogs. You can get lots of different breeds. That's no problem. There's some breeds I really like. I love golden retrievers. I think that's just a sweet breed. They're pretty and they're just nice. And God built that into the original dog kind, the capacity to get all those different breeds later on. Some kinds have gone extinct. The dinosaurs aren't around anymore. There are some kinds where certain varieties have gone extinct and other varieties remain, like elephants. Mammoths, we believe, are part of the elephant kind. They're genuinely related to each other. It's just that particular variety has gone extinct, the mammoths, and yet there are various kinds of elephants. There's the Indian elephant and the African elephant, for example, that remain. And so this is what we actually believe, okay? Animals do change within their kinds. And yes, you can get speciation within a kind. On the other hand, in the evolutionary view, there really are no kinds because the diversification of animals and plants is unlimited. And so in the evolutionary view, all organisms are related. They're all descended from a common ancestor, which would be something like a bacterium, something like that. And so in that view, you are related to broccoli. Yeah, that's your distant cousin. And I mentioned that one time. I was actually speaking to a group of atheists. By divine providence, I got to speak to them, which is kind of neat. And I pointed out, I said, in your worldview, you believe that broccoli is your distant cousin. And afterwards, one of them came up to me and said, weren't you kind of making fun of us for saying that we believe we're related to broccoli? And I said, but isn't that what you believe? He said, well, yeah. I said, well, there you go then, right? I mean, don't shoot the messenger. If that belief sounds silly, you ought to reconsider your belief. Don't pick on me for pointing it out. Anyway, I don't believe we're related to broccoli. I do believe we're related to each other. We're all descended from Adam and Eve. Now, to see which of these views is consistent with science, we need to know something about DNA. This is a very long molecule that occurs in the cells of your body. This in itself, it's just amazing, the fact that we look at the same evidence and draw very different conclusions. DNA, this very complex molecule, and it has these little, what are called nucleotide base pairs that form the rungs of the ladder. And there's 4 different kinds, and they're abbreviated by the 4 letters C, G, A, and T. A's and T's always pair up, G's and C's always pair up, but the order could be anything. And those orders spell out the instructions to produce the proteins that make you. It's kind of astonishing. And you've got 6 billion of these letter sequences in your DNA. Amazing. 3 billion, you have 2 sets of DNA and 3 billion on each set. And I mean, I think that's astonishing. We think we're clever, we can get all this information on a DVD, right? And that's pretty neat. But God put the information to make you on a molecule. That's awesome. And again, it goes to show you how our presuppositions affect the interpretation of evidence, because the discoverers of DNA, Watson and Crick, were atheists. And they looked at it and said, we've disproved God. I'm thinking, how could there be any more powerful confirmation of God than the fact that the instructions to make you are encoded on a molecule? That's awesome. It's kind of like you can spell help with beads on a rope in Morse code, right? Just by the way they're arranged. Likewise, the letters in DNA have the information to make you. And that's the same with all life on Earth. It's all DNA based if it's actual life, even plants. And so the reason a cabbage comes out as a cabbage is it's got the instructions to make a cabbage. And you've got the instructions to make a person. And aren't you glad you got the long end of the stick on that one? So, and by the way, some of the instructions are the same. And evolutionists will say, see, there you go. We must have a common ancestor because some of our instructions are the same. Well, think about this. The reason some of those instructions code for proteins, right? And we need some of the proteins from things like cabbage and other organisms for that matter. You see, God could have created unique proteins and therefore unique DNA for all organisms on Earth, but then we wouldn't be able to gain any nutrients from those other organisms. The only thing we'd be able to eat is each other. And so that would be a problem, right? So it's very important that some of our instructions are the same. It amazes me that sometimes the way that evolutionists reason in terms of these things. But yeah, we do have DNA in common with a banana, and that's why you can eat a banana and gain nutrients from it, because it has some of the same proteins you have. You have two sets of DNA. You get one set from dad, you get one set from mom. They have two sets of DNA. They got it from their parents and so on, all the way back to Adam and Eve. And the interesting thing is when a couple has children, the children will get one of the two genes from each set. You don't know in advance which one they're going to get. And so the child might get that gene from dad and that gene from mom. And then, and so they get, and then so on. You don't know. It appears to be random. And so one child might look like that, and another child will get a different set, a different combination of DNA. They're still getting the instructions from their parents, but they're getting a unique combination. And so you have a totally unique combination of DNA, unless you have an identical twin, okay? And that's why, siblings, they look a little similar, but sometimes they have some differences as well, differences in eye color and hair color and so on, because they've gotten a different combination from their parents. And this is an ingenious system because, you say, well, 6 billion instructions, that's pretty good. But when you consider the number of possible combinations, it's enormous. You take a couple like that, in terms of the number of unique children they could produce, mathematically, it's greater than the number of atoms in the universe by an enormous amount. So it's just amazing. God came up with this way of producing diversity within human beings that is absolutely ingenious. Now here it is with blood type. So if you have the combination capital A, capital letters in this instance represent dominant genes. Your blood type's A. A and O also gives you blood type A because A is dominant, O is recessive. Maybe you remember doing this in school. So those are the combinations that'll give A blood type. If you have B blood type, it's one of those combinations in the middle, either B or B and O. And then if you have AB blood type, you have one of each, and they're codominant, so they both express. The only way you can have blood type O is to have both O alleles, both O genes, because they're recessive. And so there's the 4 possible blood types for human beings. And the thing I find interesting is that if mom has blood type A, and it's what we call the heterozygous combination, where you have an O and an A, and dad has heterozygous B, where you have the O and the B, the children could have any possible blood type. Because they could get the A allele from mom, they could get the O allele from dad, and their blood type would be A. They could get the B from dad, the O from mom, and blood type B. They could get the A from mom, the B from dad, and have blood type AB. Or they could get the O from mom and the O from dad and have blood type O. Interesting. So one child might have a blood type like mom, one child might have a blood type like dad, and the other 2 children would have blood type that neither parent has. Now, it's not that they somehow miraculously evolved new information. They still got the information from their parents. They just have a unique combination. So you probably have some traits that are like your parents, whether it's eye color or hair color, whatever, and you probably have some traits that your parents don't have, but you still got the information from them. It's just because you have a unique combination, you have some unique traits. It's a very ingenious system. Here it is with the skin color. We basically all have the same skin color, brown. It's just a question of how much brown. There's a pigment called melanin. There's a couple different forms of it, but one of the forms is basically a sort of a gray pigment. And if you have these genes up in the upper left, capital A, capital B, then your body will produce a lot of melanin, and it'll spread it out over the skin, and so you have very dark complected skin. If you have the lowercase a, like in the lower right box, then you have very light colored skin. Now, if somebody down in this box, down here on the lower right, if they get married to somebody in that box, their kids are going to be in that box, right? Because the only letters are lowercase. That's the only possibility. And likewise, if somebody in the upper left box gets married to somebody in the upper left box, their kids are going to be in that box. But if you're off axis, if you're on the diagonal there, where you have, let's say, the upper right, where you have capital A, lowercase a, capital B, lowercase b, and they get married to somebody in that box, their kids could be any shade, couldn't they? Because they have all the letters available. And so we think probably Adam and Eve had a middle brown skin color, probably the combination in the upper right there. There's other ways to do it, but that's one way that that could happen. And so, they wouldn't both be very light complected, because then you'd never have the darker colors. And so this accounts for how we have the different variations that we see in human beings today. We're going to kind of focus in on dogs, because dogs have lots of variation within their genome, within their DNA, and dogs reproduce quickly, and so we can see how they vary over time. And so this is how we account for the different breeds and so on of dogs that we have today. It's just the information that God planted in the original kind, and then how that outworked over time. Now, here's the thing, though. If evolution's true, then you have something like bacteria eventually evolving into, say, a horse, as well as everything else on Earth, okay? Now, bacteria have some information in their DNA. They have the information to make bacteria. A horse has a lot more information in its DNA. It's not just that it has more DNA, which it does, but it has more information in its DNA. It's got more instructions. It's got instructions to make eyes and ears and bones and so on. Bacteria lack those instructions, and therefore they can't make those things. So it seems to me rather obvious that if evolution is true, then information has to increase, doesn't it? At some point, the instructions to make eyes and bones and so on had to be added to the instructions for the bacteria, if in fact horses evolved from something like bacteria, okay? And so evolution requires, at the very least, an increase in the genetic information. Now that's important because the processes that we observe in nature actually decrease the information in the genome. They're the opposite of evolution, and I'm going to explore some of those. And I'm not saying this is the only problem for evolution, but I'm pointing out that unless you can add new information, brand new information to the genome of these organisms, you don't have evolution. You can't do it. You're just going to get variation within a kind. And that's very interesting, because processes that evolutionists like to believe are responsible for evolution actually decrease information. And one of those processes is natural selection. You've heard of natural selection. A lot of people mistake that for evolution. They think they're the same. They're actually opposite. Natural selection is true. And it was written about by a creationist, Edward Blythe, long before Darwin. Darwin just thought that that was the mechanism of evolution, but it can't be, because while evolution requires an increase in information, natural selection only reduces the information in the genome. Let me show you how this works. Suppose you have two dogs, and suppose they have a gene for short fur and a gene for long fur, and suppose those genes have a combined effect, which some genes do, such that these dogs have medium length fur. Okay, now this is simplified, but the basic genetic principles here are true. And suppose those dogs fall in love and they have offspring. Some of the pups are going to get the short gene from mom, the short gene from dad, and they're going to have short fur. That'll happen. Some of the dogs are going to get the short gene from one parent, the long gene from the other. In fact, statistically, 50% of the offspring would have that combination, right? So they're going to have medium length fur just like their parents. And then some dogs are going to get the long gene from mom and the long gene from dad, and they're going to have very long fur. And so that happens. Now, this is a great example of variation within a kind, because we started out with dogs that just had medium length fur, and we ended up with different varieties. That's great. Do we have any new information at this point? Well, we started with information for short and long and by combination medium, and we ended up with information for short, long, and by combination medium. There's been no gain in information. There's no evolution at this point. We started with dogs. We ended up with dogs. It's not evolution. It's just dogs. Okay? Well, let's explore natural selection then. So let's suppose the environment gets very cold. And so now what's going to happen? Well, the dogs that have the shorter and medium length fur, they don't do so well in a cold climate, right? They would not like Nebraska very well. And so sadly, they die. Yeah. Now, the dogs that survive are the ones that have the longer fur because they're able to survive in that colder climate. They're well adjusted to it. And so when they meet other dogs that have survived, those will also be the long-furred dogs. And when they reproduce, what combination will the pups have? They'll have the long combination, right? And so the short-haired and the medium-haired have been eliminated from the environment because of the environmental conditions there. You see, they're not well adapted to that environment. This is a great example of adaptation. This kind of thing occurs in the world. And if an animal is not well suited to its environment, it tends to die in that environment. And so now, is this evolution, though? Have we gained any new information? Well, no, we haven't gained any. In fact, we've lost information, haven't we? Because we started out with information for short and long, and we ended up with just information for long. Natural selection is the opposite of evolution, because evolution is about increasing information. Natural selection reduces information by killing off the organisms that have information for traits that are not suitable to that environment. If the environment gets hot now, are the dogs going to ever go back to short or medium length fur? The answer is no, they're just going to die. Unless some have survived or migrated in from another part of the world, they're just going to die because that information is now gone. Now, if we started the experiment over again and you had all three varieties, and this time, let's say the environment gets very hot. So now what's going to happen? Well, now the dogs that have the longer fur, they don't do so well in that hot environment. They die from heat stroke, right? And so the dogs that survive are now the ones that have the shorter fur. They're now well suited to that environment, and so they go find other dogs that have survived because they have shorter fur, and they reproduce, and they reproduce dogs with short fur. This is a great example of adaptation. This kind of thing happens. This is not the only kind of adaptation, but it's one kind of adaptation in which a group of organisms, they shift their gene frequency to match the environment that they're in, because if they didn't, they die, you see. And so this is a great example of adaptation, great example of natural selection or survival of the fittest, but it's not evolution at all, because we started with dogs and ended up with dogs. That's not evolution, that's just dogs. And we didn't gain any information. On the contrary, we lost information. We started with information for long and short, and by combination medium, we ended up with just short. Natural selection can only remove information from the genome. That's it. That's all it does. And we find, lo and behold, that dogs that ended up in the colder environments tend to have the longer genes. Those that ended up in the hot environments tend to have the genes for shorter fur, and so on and so forth. So dogs do match their environment. We'd expect this. As the dogs were on Noah's Ark, and by the way, you'd only need 2 dogs on board Noah's Ark, right? You don't need 2 dingoes and 2 Dalmatians and 2 border collies. You certainly don't need 2 poodles, right? You just need 2 dogs. And you can get all those different breeds later. Well, by the way, the dogs we think that were on the ark would have been more like the wolf variety, because wolves still have a lot of the heterozygous combination, big A, big B, little b. So 2 dogs on board Noah's Ark, that's all you'd need. They come off, they reproduce, they split off, they travel away from the mountains of Ararat, and they carry certain genes with them. And if the genes are suitable to that environment, they'll survive there, and if they're not, they die. And some genes are kind of neutral, like eye color doesn't really have a strong effect on survival. It's just where they happen to end up. So we do find that dogs that are in the hotter environments have thinner, shorter fur. Those that are in the cold environments, thicker, longer fur. That's exactly what we'd expect. Great example of adaptation, great example of natural selection. Very poor example of evolution, because there's been no new information. No new information. This is how we account for the different varieties of wild dogs that we find in the world today. It's just the genetic information that God programmed into the dog kind, and natural selection, eliminating those traits that are not suitable to their environment. Well, what about mutations, though? Because people will say, but Dr. Lisle, evolution is not just natural selection, it's natural selection and mutation. So we got to talk about mutations. Mutation is basically a mistake in your DNA. Often when DNA is being copied, sometimes there's a copying error, and occasionally those get through. By the way, there is an editor system in your cells that can correct most mutations, interestingly. Did you know that? You have a spell checker in your DNA. And it'll correct 999 out of 1,000 mutations. Isn't that fascinating? But every now and then one gets through. We're no longer in a perfect world. And so mutations occur. Copying mistakes occur. And when that happens, it results usually in a trait that is is different because those genes have been damaged. So you have dogs that have information for 4 legs, 4 normal legs. All dogs should have that information, but there's been a copying mistake. And so some of that information is scrambled, it's missing. And so the legs don't form properly, and you end up with the dog with short, stubby little legs. That happens. That's one of the mutations that happens, or a combination of mutations that happens in dogs. And if you think about it, a dog like that little guy on the right there would not do so well in the wild, would he? Because he can't run very fast on those poor little legs, and he can't catch anything. He's more likely to be picked off by something himself. So dogs like that do not do well in the wild. Natural selection, to some extent, will weed out mutations, because in fact, some mutations are fatal, and they're immediately eliminated by natural selection. But some are just inconvenient, and so they just make it a little harder for that animal to survive, less likely for it to survive. So in the wild, mutations are kept somewhat in check. Not completely, but in the domestic world, some people like dogs that have short, stubby little legs because they can't jump up on you as much. And so people will take these little guys and they'll breed them with other dogs with short, stubby little legs, and you end up with lots of dogs with short, stubby little legs. And they don't have to survive in the wild because they have a human caretaker who will feed them and take care of them and spend millions of dollars trying to keep them alive. Okay, so my point is domestic breeds of dogs tend to be full of mutations. They really do. There's all kinds of mutations in various domestic breeds. There's a mutation that causes a dog's snout not to form properly. A dog is supposed to have a long snout. It helps with their ability to smell because the way the sense works. But there's a mutation that causes the dog's snout to be short. But the skin was designed to fit the longer snout, so it hangs off the side. If you don't clean it, it can get infected. And some people think that's cute. You ever think about it from the dog's point of view? Gee, I love having my nose stuffed into my face. That's great. Maybe not so much. Domestic breeds, they've got problems because of these mutations. Poodles, for example, they've got lots of problems because of the mutations that have accumulated in their genome. And by the way, I'm not anti-poodle. They are cute, but they do have some problems. And some of these are directly as a result of a mutation. Others are as a secondary result. One of the mutations that poodles have, dogs have a gene that regulates their fur growth. Their fur is supposed to grow so long, and then it falls out, and that controls the growth. With a poodle, that gene's been damaged, and so their hair grows forever. And that's why you have to give a haircut to your poodle every now and then. Otherwise, you'd end up with a big poof ball. And there's no way that would survive in the wild. Can you imagine that? A poodle in the wild, it's just hair everywhere. It's trying to drag all that hair behind it. It's not going to work. But you need to give them a shave every now and then. Otherwise, the hair can get in their eyes, and they can get infected, and they can go blind, or it can get in their ears, and they can get infected, and so on. It can kill them under certain circumstances. So you have to take special care of this creature because it's suffering some mistakes in its genome. Some of its traits have not formed properly. And you do have to spend a lot of money keeping these little things alive. But is this evolution, though? Have we gained any new information? On the contrary, mutations are a loss of information. That's why they have problems. They're missing some instructions. This is not evolution. It's the opposite of evolution. We've lost some information, and that's why the poor animal has some problems. And all domestic breeds have issues. They do, because they've got these mutations that we've protected. So this is how we account for the different breeds of domestic dogs. It's just the information God put in the genome and mutations, errors that have crept in over time that have resulted in some of these animals having some problems. And so this is not evolution. It's in the opposite direction of evolution. You start out with the wolf kind. We think the animals that came off Noah's Ark would have been similar to wolves because wolves still have a lot of the heterozygous genome. But then what you do when you inbreed dogs, that's what you're doing. You're concentrating those mutations until you get down to the poodle, and then that's kind of the bottom of that's kind of the end of the line there, really. A friend of mine says that you can compare this to cars, and the wolves are kind of like the Rolls Royce of the cars. They got all kinds of extra features that are just kind of nice. Windshield wipers on the headlights. Oh, that's neat. You don't really need that, but it's neat. It's a neat feature. You could remove that, and the car would work just fine. Whereas a poodle is kind of like a Kia. It's you remove one part from a Kia, it doesn't work anymore, right? That's it. That's the bottom of the line. So. This isn't evolution. It's in the opposite direction. That's the thing I want to get across to you today, is that evolution requires an increase in information. Natural selection and mutations decrease information. So you can think about it like, when I do this for kids, I say it's kind of like jelly beans. You can think of the wild kinds of dogs, lots of jelly beans, lots of information in their DNA, until you get down to the poodle, and then you just don't have a lot of information left. It's kind of the minimum amount of information you can have to have a dog still be alive. But could you turn a dog into a cat by removing jelly beans? And the answer is no, because a cat has different information. Right? It's got Jolly Ranchers. It's got different instructions in its genome, okay? And so you can't turn one kind of animal into another simply by removing information. And that's all mutations in natural selection do, is they remove information. They degrade organisms over time. So when we take a look at dogs, as one example, and we see how dogs reproduce, we find dogs reproduce dogs. How about that? Now, this is good observational science, isn't it? Testable, repeatable in the present, and it confirms exactly what the Bible teaches, that God made organisms after their kinds. And for that matter, what you sow is what you reap. Corn begets corn. You plant corn, you'll get corn. You won't get strawberries. And it really contradicts what you'd expect if evolution were true, where one kind eventually changes into another. Now, I do have to add that mutations can be beneficial by losing information. See, a lot of times evolutionists will say, well, the reason we know mutations are the mechanism of evolution is occasionally they actually help an organism survive in a particular environment. And that is true. And I'm going to just give you one example, antibiotic resistance. Because people will say, well, this is evolution in action right here, bacteria becoming resistant to penicillin or other antibiotics. Well, let me show you how this works. There's actually a few different ways this happens, but none of them are evolution. So there's a bacterium called H. pylori, there he is, and H. pylori causes stomach ulcers, and that's unpleasant. And so what you do is you go to your doctor, and he gives you an antibiotic. Now, the antibiotic is harmless to you, but it goes in and the bacteria absorbs it. And he's got an enzyme that's just part of his chemistry, part of his internal workings, that when it interacts with that antibiotic, it converts it into a poison, and the poison kills the bacterium, and you feel better until you get your medical bill. There is a mutated form of H. pylori that is missing the instructions to produce that enzyme. Now, he's got just a little bit of that enzyme, but he can't produce very much. And so when the antibiotic goes into him, it just sits there. And he survives, but he survives because he's got less information. Isn't that interesting? It's because he lacks the ability to produce that enzyme that's part of his system, or should be part of his system, that would interact with the antibiotic. He survives, but it's because of a loss of information. It's just occasionally that's helpful. And so what happens is then you kill off the ordinary bacteria, and the only ones that survive are resistant. And so now you have a strain of bacteria that's resistant to antibiotics. And they call them, they call this a superbug because it's got this resistance to it. But it's actually, it's because it's missing some instructions. And in nature, they don't compete well with the healthy H. pylori, because that enzyme they can live without it or without much of it, but it is part of their system. It helps them survive normally. It's just that in the environment of your stomach, when you're taking antibiotics, it's actually an advantage to be missing that enzyme, because it would interact with the antibiotic and kill the bacterium. So yes, mutations can be helpful, but they still lose information, and therefore they're in the opposite direction of evolution. Dr. Lee Spetner, who is a PhD biophysicist who's been studying mutations for decades, he says all point mutations that have been studied on the molecular level turn out to reduce the genetic information, not to increase it. Now, there are different types of mutations, and I've kind of simplified this. There are some mutations where a section of DNA will get duplicated. That happens. And they say, see, there's new information, right? Well, you can think of it like a paragraph in a newspaper that accidentally got duplicated. Do you really have any new information? Could you learn anything from the duplicated paragraph you couldn't learn from the original? Not at all. Just because DNA is made longer doesn't mean it has any new instructions. It's just, it now has redundant instructions. It doesn't have any new information. And in fact, Dr. Spetner says not even one mutation has been observed that adds little information to the genome. I think that's fascinating, because according to the evolutionists, we're supposed to be made of these information-increasing mutations, and yet not one has been observed. So you see, science, when we observe DNA and we look at the information in it, we find it's consistent with creation. God having created the original information in the genome, and we've lost some since then, we haven't gained any new information as the evolutionists would predict. Well, we've been talking about information. There's a whole branch of science that deals with information and how it's transmitted and how it originates and so on. And we sort of have an intuitive feel about information, but how do we define it? Well, a good scientific definition is something that Dr. Werner Gitt has worked on, and basically information always entails these three things. First of all, it always entails a symbolic code system. And so if I pick up a book, it doesn't have to be the Bible, it could be any book, and I pick it up and I turn to a certain page here and I see the word David, okay? Because I'm in 2 Samuel, so David. Now, I'm not seeing David here, am I? I'm seeing a word, David, which represents an idea. It represents a man in this case. So that's a symbolic code system. Check. The Bible counts as information, at least in that first step. But it requires more than that. It also requires language. Well, this Bible certainly has a language. This Bible's English. The Bible's originally written in Hebrew and Greek, some Aramaic. But yeah, there's a language convention there. There's syntax, there's grammar, there's rules about how the letters are to be put together and how words are to be put together and so on. So that works, that matches. And there's meaning. I could learn something when I read this text. There's an expected action on the part of the recipient of the information, that I will do something. There's a purpose for it. In this case, the purpose is that I might have eternal life. The action is that I should repent of my sins. That's the reason God wrote the Bible. That's the meaning that I take away from it, you see. If it's a cookbook, well, a cookbook would count as information, right? Because it's got a symbolic code system. It lists, it's got symbols that represent ingredients, right, by their names. There's a language convention. And there's meaning. There's an expected action. The expected action is that you will combine the ingredients in the way the book says, and the purpose is so that you won't go hungry. So a cookbook counts as information as well. And so let's test our information detection skills. So you got those three criteria: symbolic code system, language, it means something. So could this be information? Could be. It looks like we might have a code system there, right? Could be. Language, well, there could be a language. It looks like it's organized, kind of like in hieroglyphics. Is there meaning? Well, the only way to know that is to translate it. And I happen to know the translation of this. It turns out this is Genesis 1 through 5 in the form of icons. So in the beginning, you see the clipboard, like at the start of a movie. In the beginning, God created the heaven and the earth was formless and void, and darkness was over the deep, and the Spirit of God was hovering over the waters. And God said, "Let there be light," and there was light, and God saw the light, that it was good. See that? So it's Genesis 1 in the form of icons. Is this information? Yes. There's a code system, there's a language convention, and then there's meaning. It's telling us how the world came into existence. So this does fit the criteria of information. Now, it turns out whenever you identify something as having information, there are laws of nature that will apply to it. Just like when you have energy, there are laws of nature regarding energy, like the law that says you can't create or destroy energy, you can only transform it. That's the first law of thermodynamics. Likewise, there are laws of information theory. And one of these laws is that information never spontaneously generates in matter. Dr. Werner Gitt, one of the world's experts on information theory, says there is no known law of nature, no known process, and no known sequence of events which can cause information to originate by itself in matter. So if you just have a box of letters and you jumble it up like that and just shake it or whatever and you open it up, you're not going to have, it's not going to generate new information. It's not going to happen. It doesn't just spontaneously generate in matter. So where does information come from then? Oh, it can be copied, right? A Xerox machine can copy information, and a Xerox machine it's not intelligent, it's just a machine. But Dr. Werner Gitt says that information always originates in a mind. He says, when its progress along the chain of transmission events is traced backwards, every piece of information leads to a mental source, the mind of the sender. And so you can bet, if you pick up a book and it has information in it, creative information, it's telling you how to bake a cake, or it's giving you instructions on something, or it's telling you about World War II. If it has creative information in it, you can bet that it originally came from a mind. Now, the particular copy of the book that you have wasn't necessarily produced by a mind. It might have been made by a machine that makes lots of books at the same time, right? But where did that machine get its information from? A computer, probably. Where did that computer get its information from? Another computer. But ultimately, somebody wrote it, if it's got brand new creative information in it. Machines can't generate information. They can copy information. They can't create information because they're not intelligent. They don't have a mind. And that's intuitive, isn't it? I mean, if you found a book, your first inclination would not be to say, well, this probably came about by an explosion in a typewriter. You would think, well, somebody wrote this book. Maybe not this copy. It might have been made by an unintelligent machine that makes lots of copies, but somebody originally created that information. Information comes from a mind. That's intuitive. It is a law of nature. And the interesting thing is, when we apply this to genetics, we find that what do we have in DNA? We have information. Interesting. Where did it come from? Well, you got the information in your DNA from your parents. They got it from their parents. They got it from their parents, all the way back to Adam and Eve, who got it from God. So yes, the information in DNA of all organisms on Earth had to originate in a mind. And that eliminates the possibility of evolution, doesn't it? Because if information never generates spontaneously in matter, that means the information in DNA did not spontaneously generate in matter, which is exactly what evolutionists believe. By the way, in their heart of hearts, evolutionists know that information does not come about by chance. They do know that. They're just inconsistent. And I know this because I posted an article years ago on my blog, and it was called On the Origin of Articles. It's kind of a satire, and the article tries to convince you that articles do not have authors, that articles, in fact, are just a random process that happens over time, that a letter is somehow generated, and then eventually another letter, and then a word, and finally a sentence, and most of them are nonsense, but we throw those ones out. Occasionally, a correct sentence will be produced, and we say, well, that's great, and so we pass that on, you see, and then gradually articles become longer and better. And granted, lots of mistakes creep in, but we throw those ones out. So the mistakes that make the article better are the ones that are preserved. And that's how articles come about. Nobody writes them. They're produced by a slow, gradual evolutionary process, probably over millions of years. Okay? Yeah, it's a fun little article. You should check it out when you get the time. It's on not only my blog, but also on the Biblical Science Institute website. The funny thing was not so much the article. The funny thing was the responses that I got to it. Because I allowed evolutionists to comment on that article, and they wrote in, well, we know you wrote this, Dr. Lisle. I said, how? Did you see me write it? Oh, you're just taking it on faith, huh? That's interesting. Okay. Well, we could trace the IP address and prove that you posted. Well, I admit to posting it. When this thing evolved on my computer, it was just too good not to post. I had to share it with you. And but we know. How do you know? You mean you're willing to tell me that you believe in authors? You're one of those authorists that believes that articles have authors? That's just silly. I mean, that's not scientific at all. In fact, if there's an author to this article, let him show himself to me right now in the article, and then I'll believe. And which was funny because I wrote it, So I'm challenging myself to appear, and it's kind of funny. And I said, if you want to believe in authors, that's fine, but keep it in church, man. And the interesting thing was, they could have easily refuted me. They could have said, well, you or somebody wrote this because it has information in it. That's all they'd had to have said. Not one of them took that avenue. You know why? Because it would immediately eliminate evolution. They didn't want to give that up. So it was funny to watch them reduce themselves to absurdity rather than give up their belief in evolution, which they used to protect them from a God who's rightly angry at them for their sin. Or SETI, the search for extraterrestrial intelligence. We have all these radio telescopes pointed out into space, listening for alien signals. We haven't found any. I don't think we will. I don't think there's intelligent life out in space. I sometimes wonder if there's intelligent life on Earth. But here's the interesting thing, though. There are lots of radio signals in space. Did you know the sun gives off radio signals? It sounds like static. There are stars that give off radio signals. There are stars called pulsars that give off this pip, 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 pip radio signal as they spin. And so given that there's all these natural, unintelligent radio signals in space, how would you distinguish an intelligent transmission from all these natural ones? And the answer is the intelligent transmission would have information in it. It would have instructions in it. If we got information if we're listening in space and we got the signal on how to build a warp drive and we built it and it worked, that'd be pretty convincing, wouldn't it? And yet those same scientists, when they look through a microscope, when they look at DNA, they say, well, that's just chance. Isn't that interesting? The whole SETI program is predicated on the fact that information can only come from mind, and yet they deny that when it comes to evolution. Let's talk about geology now. Rock layers and how those confirm biblical creation and a worldwide flood. The first little myth we have to blow up is the idea that we know the age of these rocks, right? Because they've been radiometrically dated. And there's a lot of misconceptions about that. People have an almost godlike faith in some scientists, I think, secular scientists. And they think, well, yeah, scientists, they can date rocks because radiometric dating, they take the rock and they scan it with their tricorder and it measures the agicals and it tells you how old the rock is. Well, it doesn't really work that way. I want to show you how radiometric dating is supposed to work so you can understand the process, and then we'll see why it doesn't. You really can't date a rock scientifically. You can't. There are certain atoms that are unstable. Atoms were made of atoms, right? You got protons and neutrons in the nucleus and electrons circling around. Certain atoms of the larger varieties that are higher up on the periodic table, some of them are unstable, like uranium-238. Uranium-238 is unstable, and that means that it will spontaneously change into another atom, releasing energy. And so in the case of uranium-238, it will spit out 2 protons and 2 neutrons, and that'll convert it to thorium-234. Okay, so and you don't have to do anything. It just does this by itself. It'll sit there for a while as uranium-238, and then pop, it'll eject a helium nucleus and convert to thorium. And then thorium will sit there for a while, and it's unstable too. And so pop, it'll emit a electron or positron and convert to the next element, which converts to the next one, and so on. You don't have to do anything. This just happens spontaneously, atom by atom. And you don't know when any individual atom is going to pop, but you know statistically that after a while, the uranium will eventually turn to lead. And lead is stable, so once you're lead-206, you're going to remain lead-206 forever. It's perfectly happy to be lead-206. So you can think of it like popcorn. You don't know when any individual kernel is going to pop, but you do know that after 2 minutes in your microwave, they're all pretty much going to be popped if they're going to pop, right? And so it's the same way with uranium, except the half-life is much longer. With uranium, it theoretically would take billions of years for it all to convert to lead, but some are faster, some are slower. And so the bottom line is if you had a chunk of solid uranium and you waited for billions of years, eventually it'd be part uranium, part lead. And if you waited long enough, eventually it would be all lead. Okay? Uranium changes to lead over time. And the idea is you find a rock that's got some uranium and some lead in it, and you can use that like a clock to tell you how old that rock is. And that'll give you some assessment for how old the Earth is, because the Earth would have to be older than the rock that rests upon it. So that's pretty neat, right? So you find a rock that's got some uranium, some lead. We know the rate at which uranium changes to lead. You work the problem backwards and figure out when it was all uranium. But wait a minute, how do you know that rock was all uranium to begin with? Maybe it had some lead in it to begin with. In which case your age estimate would be inflated. And by the way, secularists do not assume that the rock was all uranium to begin with. They know it had some lead in it to begin with. Well, how much lead should we start with? Well, you tell me how old you want the rock to be, I'll tell you how much lead it started with. You see the problem? You can think of the uranium changing to lead like sand going from the top chamber to the bottom chamber in an hourglass. And you can use an hourglass to tell time under certain assumptions. If I had an hourglass going when you first came in here and it looked like that, and I asked you, how long ago did I turn that over? You say, well, it's an hourglass. It's about halfway through. Half an hour. Pretty good, right? I said, oh, I got you, because in fact, I turned it over only 1 minute ago, but already a lot of the sand was in the bottom chamber. Okay? So that's an assumption of initial conditions. How do you know the initial amount of uranium to lead? And by the way, and there are techniques that secularists use to try and get around that, but the fact is you don't ultimately know the initial ratio of the elements. You don't, because you weren't there when the rock formed. How do you know that somebody didn't add sand when you weren't looking or remove sand? Uranium's leachable in salt water. It can move in and out of the rock. Interesting. And if you don't take that into consideration, your age estimate will be wrong. How do you know the throat of the bottle's always been the same size? That's probably pretty realistic for an hourglass, right? But we don't know that the rate at which uranium changes into lead has always been constant throughout Earth history. In fact, there is very compelling evidence that it has not been constant throughout Earth history. There are certain kinds of radioactivity we can speed up in a laboratory. The reaction from, rhenium-osmium reaction has been sped up in a laboratory by a factor of 1 billion. We can make it decay 1 billion times faster. And there are probably natural ways to do that as well. So my point is, radiometric dating is based on a number of assumptions that you can't ultimately know. The idea that we know the initial conditions, the ratio of uranium to lead, the idea that the decay rate has always been constant throughout history, you don't know that, and there is some evidence against it, or that the system is closed, and so uranium has not moved into or out of the rock. If any one of those is wrong, your age estimate will be wrong. And the interesting thing is, regardless of these details, if you remember these or not, we've tested radiometric dating on recent rocks. When Mount St. Helens erupted in 1980 and subsequent eruptions, it formed brand new rocks. And radiometric dating is supposed to tell you when the rock hardened, because when it's liquid, the elements can flow in and out. But when it's hardened, that's supposed to trap them in. It sets the 0 point of the clock. Well, we took some rocks from Mount St. Helens and sent them into secular labs so we couldn't be accused of bias, and had them radiometrically dated. And those rocks came back with age estimates of hundreds of thousands to millions of years on rocks that in fact are just a few years old. You say, well, that's an anomaly. That's just, well, the same thing's been done with rocks from Hawaii. You take a rock from Hawaii, a brand new rock, you can stick your pole in the magma, right, or lava, and pull it out, let it harden, send it into a lab. You'll get millions of years for a rock that you saw form. Isn't that interesting? There are different methods, there are different ways of doing this, but the fact is they do not produce consistently right results on rocks whose age is known. Radiometric dating has been shown to not work on rocks of known age, and yet secularists assume that it works on rocks of unknown age. I don't find that to be very logical. In fact, there are some methods, the isochron method, where you can actually get a negative age, which I think is interesting. You can hold in your hand a rock that, according to radiometric dating, has not formed yet. That happens. Interesting. That's the bottom line. What about carbon dating? Carbon dating is better. Now, it's not perfect either, but it's better because, at least with carbon dating, when we test it on things of known age, it tends to give close to the right answer, within a factor of a few, within a factor of 10 maybe. And the way carbon dating works, it's similar. Most carbon is C12, and C12 is stable. It'll remain C12 forever. But there's a certain variety of carbon, C14, that's produced in the upper atmosphere when cosmic rays bombard nitrogen atoms, converts them to C14. C14 is unstable. Those 2 extra neutrons make it unhappy, and it will want to convert to nitrogen, which it does spontaneously with a half-life of 5,700 years. So you have a chunk of solid C14. After 5,700 years, half of it will be nitrogen. It'll have decayed away. And after another 5,700 years, another half, and so on. And after 1 million years, you don't have a single atom left. And it's produced in the upper atmosphere. So it's part of our atmosphere. There's some carbon, 14 in this room right now. And when you're alive, you eat food. The plants take in the C14 from the atmosphere, and they incorporate that into their structure. The animals eat the plants. We eat the plants, or we eat the animals that ate the plants. And so some of the carbon in your body right now is C14. So you're all slightly unstable. What do you think about that? And it's always decaying back into nitrogen. But when you're alive, you continue to replace it. You take in new food, and you breathe. And so you're constantly replenishing your supply of C14 when you're alive until you die, and then you don't replenish it anymore. When you die, it just decays away. So what you do is you can measure the total carbon in a specimen. You measure the C14 to C12 ratio, and it'll tell you how long ago the thing died. When you're alive, it remains constant, C14 to C12, because you're constantly replenishing it. And then when you die, it just fades away. And so, and when we carbon date organisms, we find, yeah, they're within the biblical timescale. Carbon dating is our friend. It confirms biblical creation, even on things that evolutionists believe to be millions of years old, like coal beds. You can take a chunk of coal supposed to be 100 million years old. It shouldn't have any C14 in it if it's millions of years old. But you test it, there's C14 in it. Every one we've checked has C14 in it, which tells me it's nowhere near millions of years old, because after 1 million years, you wouldn't have one atom of C14 left. If the entire Earth were made of C14, after 1 million years, not one atom would be left, apart from a recharging mechanism. We've found it in diamonds. Diamonds that secularists believe to be 1 to 2 billion years old. They can't be that old, though. They have C14 in them. C14 doesn't last that long. It doesn't even last millions of years, let alone billions. It confirms that the world's thousands of years old. There are lots of processes like that confirm, maybe they don't prove in an absolute sense, but they're consistent with what you'd expect given the biblical age of thousands of years that God created in 6 days a few thousand years ago. The rate at which salt fills the ocean. Even fresh water has a little bit of salt in it, which it picks up from the land, from the continents, and then it dumps that into the ocean. The water evaporates, but it leaves the salt. And so every year the oceans get very slightly saltier. And if that's been happening for billions of years, you got a problem, because when we work the math backwards, you figure out how much salt the ocean had in the past. Once you get over, even being generous to the critics, once you get up to 62 million years, it's zero. And you can't have less salt than zero salt, right? So that's an upper limit. And yet the secular age of the ocean is supposed to be 3 billion years. According to the scripture, 6,000 years, something like that, 1,000 years ago. But the amount of salt content limits it to less than 62 million. Now, 6,000 is less than 62 million, but 3 billion is not less than 62 million, right? So that's a problem in the secular view. The rate at which mud accumulates on the ocean floor, we can measure that too. It's about 20 billion tons a year. You can maybe get rid of a little bit of it with plate tectonics, but at best 1 billion tons a year. So the other 19 billion tons simply accumulate. How long does it take to get Earth's current amount of mud on the ocean floor? At the current rate, 12 million years, maximum. And that's assuming there was no mud to begin with, and it assumes there was no worldwide flood, which would dump a lot of mud on the ocean floor quickly. And yet that's still inconsistent with the secular age of 3 billion years. But it's perfectly consistent as an upper limit if the world's thousands of years old. Human population. How long does it take to get Earth's current population from 2 people? It doesn't take millions of years. And yes, you have to include for higher mortality rates in the past and so on, but it's very consistent with the biblical time scale. And we have records where we can estimate that at least, and it's consistent with biblical creation. But the best evidence that the world's thousands of years old is we have the birth certificate of the universe. That's what the Bible is, at least Genesis, and it's repeated in Exodus 20:11. For in 6 days the Lord made the heaven and the earth, the sea and all that's in them. God knows how long it took for him to make the earth, and he's recorded that information for us. And so what it comes down to is the secular scientists say the earth's billions of years old, take my word for it. God says, I created in 6 days, take my word for it. That's really the issue. And we've seen the science lines up with what the Bible teaches, but again, it's all a question of your presuppositions, how you look at that evidence. But what about the fossils then that we find in these rocks? Because I was given the impression that fossils take a long time to form, but here you have a fossil ichthyosaur. Apparently this happened pretty fast because it was killed and buried in the process of giving birth. You see the baby ichthyosaur being born there? They're born tail first because they're air breathers, they're reptiles, they're swimming reptiles. So as soon as it's born, it has to swim to the surface and get its first breath of air, which is kind of interesting. So, yeah, that must have happened relatively fast. You can even see some of the stomach contents that are not yet digested. There's a fish fossilized in the process of eating another fish. So very interesting. Apparently it doesn't take millions of years for these things to happen. It seems like they've happened catastrophically. Most things don't fossilize. You understand? People think, well, you know, an animal dies and then it just slowly fossilizes over millions of years. Most things don't. And you know that. You've seen an animal left on the side of the road, like our dead cat Earl here. And we're just going to wait and watch him slowly fossilize over millions of years, right? Oh, you wait a few days. Well, now he's a smelly dead cat on the grass. You wait a few more days, very smelly dead cat on the grass. You wait a few more days, part of him's missing. You wait a few more days, more of him's missing. You wait a few more days, all of him's missing. Yeah, that's what happens, right? You've seen that. You've seen that happen. Animals don't just become statues over millions of years. They decay. They're recycled back into the environment, and I'm very grateful for that. But even then, see, to get something to fossilize, you have to bury it to protect it from the elements. Okay, and even then I was given the wrong impression because we find fossil fish all over the world. And I was taught what happens is the fish dies, sinks down to the bottom, and then over millions of years, sediment covers it, you know, so that one layer of sediment happens the millions of years after the next. Well, that doesn't make any sense because if that layer of sediment happened a million years after that one, the top of the fish would have had plenty of time to decay because it's exposed to the environment. You have to cover the whole thing quickly in order to get fossilization to happen. And most fish float anyway, and they're picked off by scavengers, and they don't just fossilize, right? When you've probably seen, you know, National Geographic or Discovery Channel where they go down to the bottom of the ocean. I love those things where they go down to the bottom of the ocean. You don't see billions of dead fish fossilizing on the ocean floor. You don't see that. If you do want to form a fossil fish, here's how you do it. You go home to your aquarium, and you dump some concrete in it, okay? And it's going to kill a fish, of course. It's going to bury him quickly, And because you have a cementing agent there, it's the mud is going to become rock, basically. That's what concrete is. It's artificial sedimentary rock. And usually what happens is there's enough bacteria left that they can still decay away the outer portion, the fleshy parts of the fish, but not the bone. And so the minerals will then move in and fill in the little holes in the bone. Bone is porous. It's very light. Fossils are heavy because the minerals have come in and filled in all the holes in the bone. And there's your fossil fish. And it doesn't take millions of years. Not at all. It happens quickly. What about the kinds of fossils that we find? Do we find evidence of evolution? Well, no. We find variation within a kind. We find different breeds of horses. We find different breeds of camels. We find different breeds of dogs in the past. That's what we find in the fossil record. We don't find a non-horse evolving to a horse. People say, well, here you go, the evolution of the horse. And see, the feet are a little different on those ones. And the number of ribs is a little different, and so on. By the way, if you put it in the order of feet, thinking that it evolved that way, it's different than if you put it in the order of number of ribs. Interesting. So you can't have a consistent evolutionary path there. These are just different breeds of horse. That's what they are. See, but that one on the end there, that one's real small. But there are breeds of horse today that are very small. These are both adult horses. They're just different breeds. There's lots of variation within the horse kind. Some varieties have gone extinct where their feet were different. Instead of having the single hoof and they had the three where it splits off. But there's lots of varieties of horse today. That's not evolution, that's just horses, right? Variation within a kind is what we see in the fossil record. What about the rocks in which these fossils are found? Don't rocks take millions of years to form? Here's a set of car keys embedded inside solid rock. I don't think that took millions of years to form. Here's a man-made clock embedded inside solid rock. At least we know when it happened, right? That's the one rock we know right when it formed. All these layers. Not all those are rock, but a lot of them are rock, and yet those did not exist before 1980. Those were formed in the Mount St. Helens eruptions. And there's a person down there for scale. Oh, surely those took millions of years, right? No, that sediment was deposited quickly, and some of it has, the conditions weren't ideal for forming rock, but some of them have solidified into rock at this point. And you even have a canyon there. This is all produced by that Mount St. Helens eruption. Pretty amazing. And it carved out a canyon 1/40th the scale of the Grand Canyon in a matter of hours. It doesn't take millions of years to form canyons or the rock layers around them. It can happen quickly. See, they used to say that these fine layers that you find in sedimentary rocks, those are annual. 1 year, 1 year, 1 year. You add them up, millions of years. See? Well, I'm afraid all those were produced in the Mount St. Helens eruption. So they're not annual at all. And those are the same kinds of layers you find in the Tapete sandstone, which covers much of the United States, cuts through the Grand Canyon. Continental scale deposit. That's interesting. So whatever laid down those layers was, covering the entire continent. A worldwide flood would do that, wouldn't it? Yeah. We find trees buried vertically in sediment. They used to say, well, coal forms in swamps, right? Peat accumulates at the bottom of the tree, because you'll find coal a lot of times with trees like that. There's some coal at the bottom. But the interesting thing about these trees is that they don't have roots. And that's a little surprising, because don't most trees have roots? I mean, that's kind of interesting. But we now know how this happens, and it has nothing to do with millions of years. It has to do with catastrophe. When Mount St. Helens erupted, it produced this kind of phenomenon. What it did is it uprooted trees because of the explosion, and that's why they don't have roots. They have little remnants of roots, but they don't have full root system. And there's a lake next to Mount St. Helens, Spirit Lake, and most of the logs would float vertically. A few of them would be horizontal. Most of them would be vertical. And as they become waterlogged, they would sink down to the bottom, and then they're covered with sediment left over from that explosion. And so that's how this happens. It has nothing to do with millions of years. It has to do with catastrophe. It's flood conditions that do that. So again, when we take a look at the rock layers and how they form, we find that good observational science, at least the kind we can test today, it confirms biblical creation and a worldwide flood. It's consistent with it. It's consistent with what we'd expect. And so when you see these rock layers, you shouldn't be thinking millions of years. You should be thinking, wait a minute, worldwide flood. God judges sin. That's the real meaning of the rocks. The real meaning is repent. That's what they mean, right? And it's interesting because the Bible predicted that people would come and deny the worldwide flood. It says that for this they willfully forget. They're deliberately ignorant that by the word of God the heavens were of old and the earth standing out of water and in the water by which the world that then existed perished, being flooded with water. It says they're willingly ignorant of that worldwide flood. And that's exactly what we're seeing today. It's exactly what we're seeing. But if you understand this, if you understand science confirms biblical creation, then if you're not a believer, you got a problem. Because you realize, wait a minute, it's because of what Adam did that the world has been plunged into darkness. I've got a problem because I've sinned just like Adam has. God can't let me into that new creation, that very good creation, because I'd ruin it the same way Adam ruined the original. That's a problem for us because we've all sinned. But of course, God made a way of escape. Jesus Christ took our payment on the cross. And if we trust in him, if we repent, trust in him, he's offered to pay that penalty for our sins. He's already done it. And so we just need to receive that. God is a righteous God, and therefore he will judge sin. That's the whole point of the flood, really. The wickedness of mankind became great to the point that God wouldn't tolerate it anymore. But God's also merciful, and he provided a way of escape. And in Noah's day, that was the ark. That kind of, really is kind of a picture of Christ, isn't it? Because the ark gave Noah physical salvation from a physical disaster, whereas Jesus gives us spiritual salvation from the both spiritual and physical disaster to come. And so I think it's interesting, too. The Bible says Noah was a preacher of righteousness. So he was out there preaching, come on board the ark and be saved. And yet, of all the people in the world, and there could have been billions of people in the world at that point, by the way, if you do the math. Could have been as many as today. And yet 8 were saved. 8 responded to God's message of repentance and mercy. And they were Noah's immediate family, interestingly. And then God closed the door on that ark. I think that's significant, too. God's the one that decides time of grace is over, time of judgment begins. And we don't know when that is for each one of us, which is why today is the day of salvation. So I never like to end without reminding people about the gospel message that Christ does offer salvation for forgiveness of sins if we just trust in him. We do have this presentation available on DVD, Creation Science Confirms the Bible. And then the one from last night, we have that not only on DVD but on book format as well, which I think, I'm a reader, so if you like that. But we do have the DVD of that as well. We may or may not have this in stock. Understanding Genesis, which we'll cover tomorrow morning in the main service. How do we understand Genesis? Does it really mean 6 days? Well, we'll talk about that. Taking Back Astronomy, which we'll cover Sunday evening, and how all that works. Discerning Truth, how to spot logical fallacies and arguments that evolutionists make. Evolution and Logical Fallacies, the DVD that goes along with that. Again, we have books on my specialty field of astronomy, Stargazer's Guide to the Night Sky, how to better enjoy the night sky from a Christian perspective, if you want to know what the constellations are and which one's Saturn anyway. And if you want to get a telescope, what kind you might want to get, how to use it, and so on. Created Cosmos DVD takes you on a tour through the universe from a biblical perspective. That's just a fun program. It's the planetarium show I wrote for the Creation Museum. And his star, what about the star that guided the Magi to Christ? You ever wonder what that is? Well, I got a DVD on it. And yes, I've seen the other one, and it's not accurate. So I produced this one. Hopefully this one will do a little better. Creation Evangelism, how to use creation to share the gospel more effectively. There's a good way to do it, and that DVD explores that issue. Keeping Faith in an Age of Reason answers 420 alleged Bible contradictions. Not one of them is legitimate. Physics of Einstein. What about black holes? And what about distant starlight? How did God get the light from the galaxies to Earth and the biblical time scale? We'll hit that Sunday evening, but the book goes into more details on that. I included math sections for those who are adventurous, but I put them in boxes so you can skip the math if you want to. And it's written for laymen, so you can all read it, hopefully. You can get all the DVDs together for a discount. You can get all the books together for a discount, or you can get everything together for a discount. And I forgot to include a slide for it, but we also have a new logic curriculum that I think is really neat. It shows you how logic is rooted in the Christian worldview, and it takes you through common logical fallacies, mistakes that evolutionists often make, and so on. And we do have, of course, our free monthly newsletter. Don't forget to sign up for that. It is free, and it is email, so make sure you put your email address and do so legibly, or you'll get nothing. Check us out as well on the Biblical Science Institute website, and thank you very much. We'll come back at, I think it's 11, right? So thank you.